A giant, 4 million times the Sun black hole sits at the center of the Milky Way, normally quiet, but if it woke up, the sky would put on a show and a few of our modern conveniences might act oddly. Think of it like someone tossing a flaming log onto a distant bonfire. The light gets brighter, sparks fly, and the smoke can travel far. In space, that spark is intense light and high-speed particles. Some of that could reach Earth and tinker with radios, satellites, and the glow of the night sky. Not a Hollywood apocalypse, but definitely noticeable. Why watch this? First, I'll walk you through what we'd actually see from here, how fast the effects would arrive, which everyday things, GPS, satellite TV, phone signals, could glitch, and which doomsday rumors you can safely ignore. Plus, a few surprising real examples from past cosmic outbursts that looked a lot like fireworks through a telescope, and a tiny joke about your pizza surviving the ordeal. Stay tuned and you'll know what to worry about, what's just cosmic drama, and how astronomers would spot the trouble first. A quick tour of Sagittarius A and why astronomers care. At the center of the Milky Way sits Sagittarius A*, a supermassive black hole roughly 4 million times the mass of our Sun, and it dominates the motions of stars in its neighborhood. Light itself bends and twists near it, so astronomers study the way nearby stars orbit to learn how strong gravity behaves up close. Telescopes that work at radio, infrared, and 10th-ray wavelengths are needed because dust in the galaxy blocks visible light, which is a bit like trying to see through fog with sunglasses on. The black hole is usually quiet, but it does flare. Occasionally it brightens in 10th rays and infrared, like a normally calm campfire suddenly popping and spitting sparks. Gas and dust that fall toward it form a hot, swirling disk called an accretion disk. Picture water spiraling down a drain, glowing and heating as it moves inward. Sometimes material gets launched away in narrow streams called jets. Think of a garden hose spraying after you step on it. The mechanics teach astronomers how energy moves in extreme environments. Why everyone watches Sagittarius A** so closely is practical. It is the closest supermassive black hole we can study in detail, making it the laboratory for theories about how galaxies and black holes affect each other. Observations of stars whipping around it, some moving at a few percent of the speed of light, let scientists test Einstein's predictions in a strong gravity setting, like checking whether the ruler is straight when the room itself is bending. Understanding its feeding habits helps explain how active black holes light up whole galaxies elsewhere. The quiet behavior of Sagittarius A** shows what a low-energy galactic center looks like. Modern techniques give clear, surprising views. Networks of telescopes around the world work together to produce extremely sharp images, and instruments that track infrared light follow individual stars on tight orbits. That combination turns a distant, invisible monster into something you can measure and model, which is why astronomers care so much. Studying Sagittarius A** is about learning the rules that govern the most extreme engines in the universe, using the closest example we have. What active means for a supermassive black hole. Gas pouring toward a supermassive black hole can light up the center of a galaxy in a dramatic way. The black hole itself still swallows light, but the stuff spiraling in heats up and shines, turning a normally quiet object into a bright beacon. Think of it like water going down a drain. The drama happens in the whirlpool, not in the drainpipe. That hot, spinning layer of gas and dust is called an accretion disk, which is basically a cosmic frying pan where friction and compression make the gas glowing hot enough to emit visible light, ultraviolet, 10th rays and radio waves. The glow is only one part of the show. Fast, narrow jets of particles can be launched away from the poles, punching far out into space like garden hoses spraying across a lawn. Those jets are powered by the motion and magnetic fields in the accreting gas. They can carry enormous energy and plow through the galaxy's gas, and sometimes they keep going well past the galaxy itself. In plain terms, it becomes both a bright lamp and a powerful blowtorch. Brightness can change too, sometimes steady and sometimes flickering like a campfire that suddenly spits a spark. Astronomers recognize an active nucleus by a set of telltale signs. A bright core that stands out in many kinds of light is one clue. Strong 10th rays and radio signals are another. Fast-moving gas close to the center makes characteristic spectral features, basically different colors smeared out by speed, so the light carries a fingerprint of chaos. Dust heated by the central engine shines in the infrared, so a single object can be noticeable from radio waves to visible light to 10th rays. It's like hearing a car from its engine noise, seeing its headlights, and smelling the hot rubber all at once. Nothing magical awakens the black hole, activity is driven by feeding. When lots of gas and stars wander close enough, they supply material that spirals in and turns on the light. That feeding can also shape the galaxy. Outflows and jets can heat or eject gas, slowing down the formation of new stars, or sometimes compress gas and prompt a burst of star birth. Picture a heater in a room that either warms everyone up and slows them down, or a leaf blower that clears the yard. The central black hole's energy can regulate its surroundings in similarly practical ways. And yes, the universe has a sense of humor. On cosmic scales, a very hungry object behaves a lot like an overeager kitchen appliance. From sleepy to show-off, how black holes wake up. Black holes can switch from being quiet to suddenly energetic when they start gobbling up a lot of nearby gas or a stray star. The core idea is straightforward. When fresh material falls toward the black hole, it forms a spinning pancake of hot gas around the hole, and that spinning gas shines brightly before crossing the point of no return. In everyday terms, think of a drain that usually runs slow but spits and bubbles when a big clump of hair goes in. The drain itself doesn't change, the supply does. One common trigger for wake-ups is a wandering cloud of gas drifting too close. This gas gets stretched and heated as it spirals in, giving off light from radio waves up through 10th rays. Another dramatic trigger is a star that gets too near. Tidal forces can tear the star apart in a violent process that produces a bright flare visible across great distances. Galaxy collisions or close passes also act like a grocery run. Gravity scrambles the orbits and funnels fresh fuel toward the center, supplying the black hole with a banquet it didn't have before. Sometimes the change is a short-lived flare, and sometimes the feeding continues for a long time until the pantry is empty. Magnetic fields play a surprising role, and they do so without any drama backstage. Twisted magnetic lines in the spinning gas can give some particles a one-way ticket outwards at nearly light speed, forming narrow jets that shoot far beyond the galaxy. Those jets are the show-off part, bright, focused, and able to affect regions well away from the black hole. Picture a garden hose with a nozzle. Loosen the nozzle and the spray spreads, pinch it and you get a focused stream. Magnetic fields pinch and direct the gas into streams. Not every close encounter leads to fireworks. Sometimes a gas cloud passes by and only causes a little flicker, because the gas may be too diffuse or moving too fast to be captured effectively. Observers have seen the central black hole of our galaxy mostly quiet but punctuated by small flares, which shows how variable and picky the feeding process can be. These flares are like brief bursts of applause from a usually reserved performer. When a black hole becomes active, it doesn't just put on a light show, it changes its neighborhood. Powerful winds and radiation can heat or blow away the gas that normally forms new stars, slowing star formation in the host galaxy. This is like turning a warm oven on in a bakery and then blasting cold air into it. The dough won't rise properly. The larger environment responds to the black hole's appetite in surprisingly direct ways. Scientists watch multiple wavelengths of light to know when a black hole is waking up. Optical telescopes show brightening in visible light, radio dishes catch jets, and 10th-ray instruments detect very hot gas near the hole. Combining these views gives a fuller picture, just as listening, looking, and smelling a sizzling pan tell you it's time to flip the food. The complexity is high, but the core mechanics, more fuel, faster spin, magnetic action, are intuitive and repeatable across many galaxies. Fueling the beast, gas, stars, and that mysterious cloud G2. The black hole at the center of the Milky Way feeds when material wanders too close and gets trapped by its gravity. Gas blown off nearby stars, stray clouds of dust and gas, and whole stars that get a bit too adventurous are the main things that can end up as the black hole's meal. In the crowded center of our galaxy there are many massive, young stars that continually shed material, think of them as windy teenagers blowing off outer layers, and some of that wind can drift inward toward the black hole rather than escaping into space. Stellar winds act like a slow, steady drizzle of fuel. A big star near the center can lose a steady stream of particles that, under the right conditions, cool and clump together. Those clumps behave like leaves or twigs swept into a gutter and eventually pushed toward the drain. Here the drain is the black hole. Because the gas usually carries angular momentum, it's moving sideways as well as inward, it rarely plunges straight in. Instead it forms a swirling disk and slides inward bit by bit, losing its sideways motion through collisions and friction. The process isn't glamorous, it's more like a traffic jam where cars slowly inch closer to the exit than a sudden freeway plunge. Whole stars can also become fuel, but only if they stray too close. A star that wanders into the black hole's strong gravity can be stretched and torn apart, spilling its innards outward in a dramatic spray of gas. Astronomers call that a tidal disruption event, which is just a fancy way of saying the star gets pulled like taffy until it falls apart. Sometimes a star loses only some outer layers and keeps going, slightly embarrassed and lighter. In a crowded neighborhood, collisions between stars or interactions with compact objects can fling material outward, too, providing more snacks for the central beast. Then there's G2, the mysterious cloud that brought this feeding process into sharp focus. At first it looked like a simple gas blob on a collision course, and many hoped it would produce a fireworks show of radiation as the black hole gulped it down. But G2 behaved differently than a loose cloud would. It held together, more like a dusty cocoon around a star than an unruly gas blob. That survival told astronomers something useful. Not every approaching object becomes a feast, and some of these clouds are actually stars wearing heavy coats of gas and dust. Observing G2 up close was like watching someone approach a campfire wearing a puffy jacket. The jacket may catch a little, but the person can stay intact. As material finally gets closer, it turns into a hot, glowing swirl. Friction and tangled magnetic fields act like brakes, turning ordered motion into heat and light. The result can be brightening across many wavelengths if enough fuel arrives at once, but most of the time the feedings are drip, not gulp. So even if the center of our galaxy seems quiet now, it's simply because the black hole isn't being handed many big, soft snacks at the moment. And if it does get a hefty meal later, it might belch out a dramatic flare, at which point astronomers and telescopes will be ready, binoculars in one hand and a bowl of popcorn in the other. Accretion disks explained with popcorn analogies. When gas and dust swirl toward a black hole, they don't fall straight in, they spread out into a thin, spinning disk that heats up as material rubs against itself and falls inward. Think of the disk as a huge, cosmic hotplate and the bits of gas as popcorn kernels sliding and bumping around on it. As those bits rub and squeeze against one another, friction turns their motion into heat, and that heat is what makes the disk glow in visible light, ultraviolet, and 10th rays. Like kernels in a pot, some parcels of gas get jostled and warmed slowly until they glow steadily, while others surge suddenly and release bursts of energy. Picture a kernel that suddenly pops and jumps away. In the disk, that pop is not literally corn bursting but a sudden bright flare when pressure or magnetic effects let stored energy escape quickly. You can compare the slow heating to watching a saucepan simmer and the sudden flares to the occasional loud pop of an unsteady popcorn batch. It gets noisy in a metaphorical way, and astronomers spot those little bursts as flickers in the light from the center. Because angular momentum must be conserved, material in the disk acts like people on a crowded merry-go-round. Those nearer the center move differently than those farther out, and the only way for some gas to move inward is for other gas to move outward. Some kernels are nudged outward and end up flung away, much as popcorn sometimes flies out of the pan. That outward moving matter can form winds or be launched along the black hole's poles as narrow, fast streams. Think of tiny, focused popcorn jets, while the rest steadily feeds the growing, hungry center. Simple kitchen examples help lock the idea in. Stirring coffee makes the surface spin and slosh, bits of foam spiral inward and outward, trading places as they rub together. A roundabout full of cars does the same. Cars slow or speed up slightly when drivers change lanes, transferring momentum, and this allows others to drift inward. With a little humor, the black hole is no movie theater, there's no buttered popcorn surviving those conditions, but the popcorn image is handy for teaching. It captures how heat, collisions, and sudden releases of energy work together to shape the bright, weirdly lively disks that feed active black holes. Jets and outflows, the galaxy's internal fireworks. Sagittarius A*, the Milky Way's central black hole, can fling out narrow streams of particles and broader winds when it swallows gas and dust. As the material spirals in, it forms a flattened, fast-moving whirlpool that heats up and shines. Some of that energy gets redirected and shoots away along the black hole's poles. Think of it as a cosmic blender with a couple of very focused spouts. One makes a thin, high-speed jet like water from a hose, and the other is a wider, Messier puff like steam from a kettle. Those narrow jets are composed of charged particles racing along tangled magnetic lines, and they often show up strongly in radio waves and 10th rays. They can punch through the dense gas around the center and light up as they slam into clouds, forming bright knots and ripples. The broader outflows act more like a broad wind, pushing and heating gas over a large volume. A real-world comparison is a leaf blower versus a garden hose. One sculpts and compacts, the other sprays a steady stream. Evidence that our galaxy has experienced similar activity before includes large bubble-shaped structures rising above and below the galactic plane, carved by past energetic outflows. The consequences for the surrounding galaxy are mixed and surprisingly human scale in how they behave. When a jet compresses a cloud, it can squeeze gas into denser clumps and trigger new stars, like a gardener nudging soil into neat rows. But when an outflow strips gas away or heats it too much, star formation can stop, more like using a leaf blower to scatter seedlings before they can grow. In addition, these energetic winds boost cosmic rays and alter the chemistry of gas clouds, changing what kinds of molecules can form. Picture a kitchen where the heat is suddenly turned up and the flavors change. Astronomers watching an awakening Sagittarius A** would see the center brighten across many wavelengths, with moving features and expanding bubbles. It would be a slow-motion fireworks display, dramatic but not the kind you'd see from your backyard unless you were very, very far away. Telescopes that catch radio waves, 10th rays, and gamma rays would be the best seats, and the show would teach us about how black holes shape their neighborhoods. On a lighter note, the galaxy would get a new interior decorating scheme, dramatic jets, sweeping outflows, and a central spin that even the most ambitious fireworks designer would envy. Radiation types: radio, 10th rays, gamma rays, and more. At roughly 26.0 light-years away, the center of our galaxy already emits in many parts of the spectrum, and if the black hole there became much more active, different kinds of radiation would brighten in distinct ways. Radio waves would be among the easiest to detect. They are the long, low-energy waves similar in spirit to the ones used for FM radio but at much different frequencies. Telescopes like dish arrays would see a stronger, fuzzier glow and possibly jets that broadcast in radio for thousands of light-years, sort of like turning up a distant car stereo so the bass rumbles across town, harmless to your ears, but a big deal for astronomers. In everyday terms, radio emission from an active galactic center would interfere with sensitive radio observations the way a loudspeaker in the next room ruins a quiet phone call. It wouldn't wipe out your Wi-Fi, because the frequencies and strengths are very different. Moving up in energy, infrared and visible light would also rise as gas heated by the black hole glows like a very hot stove element. The infrared band is heat radiation you can't see but can feel with special cameras. Astronomers use it to peer through dust that hides the center. If the black hole fed on a chunk of gas, that gas would heat, radiate in infrared and visible wavelengths, and make the center brighter to telescopes tuned to those bands. Think of it like a campfire that gets bigger and sends light and warmth farther. The warmth, infrared, travels and the light, visible, can make the sky a little more interesting from an observer's point of view, but not dramatically change daylight for us. 10th rays would be the dramatic flares everyone notices next. These are high-energy photons similar in type, though not in scale, to the 10th rays used in hospitals. When gas falls very close to the black hole, it gets squeezed and heated to extreme temperatures and can emit 10th rays, sometimes sudden increases, flares, light up the region in tenth rays for short periods. For satellites and instruments in orbit, an uptick in tenth rays and related particles can increase noise, disrupt some electronics, and create extra background that makes observations of other objects harder. People on the ground can picture this like sunspots and solar flares causing radio blackouts. The mechanism is different, but the practical result, interference with space-based systems, is similar. At the highest energies, gamma rays and cosmic rays would tell the tale of the most violent processes. Gamma rays are the most energetic kind of light and are commonly produced when very fast particles slam into fields or photons get boosted to extreme energies. A black hole launching jets or accelerating particles near its event horizon can make gamma rays through collisions and particle interactions. Cosmic rays, fast protons and atomic nuclei, can also be accelerated and rain out into the galaxy. For everyday life on Earth, the distance helps a lot. Most of these particles spread out and lose punch by the time they reach us. However, satellites, high-altitude aircraft, and astronauts could see increased particle hits, which is like turning up the level of static and occasionally frying a tiny chip if protection isn't sufficient. Different production mechanisms make different fingerprints. Thermal emission is like a piece of metal glowing because it's hot. It produces infrared and visible light. Charged particles spiraling in magnetic fields give off radio and sometimes tenth ray emission in a process that is like a humming electric wire making noise when you tune a radio. And collisions or boosting of low-energy photons by very fast electrons, picture a ping-pong ball getting a hard tennis ball strike, can turn lowly infrared photons into tenth rays or gamma rays. Observers use these fingerprints to figure out whether what they see came from hot gas, fast particles, jets, or shocks. Practical examples help. Radio observatories would notice a louder, more complex signal and might have to filter it out when studying faint galaxies. Infrared telescopes would see more glow through the dust and could use that to map how gas is falling in. Tenth-ray monitors would register spikes and possibly advise satellite operators to take precautions, much as they do during strong solar storms. Gamma-ray detectors would look for bursts and extended emission that point to particle acceleration. A touch of cosmic humor, the black hole wouldn't be changing your toaster settings, but it might make astronomers very excited and system administrators a bit nervous. Timescales of awakening, flares, eruptions, cosmic hiccups. Sagittarius A** can give off tiny, quick bursts of energy that last only minutes to hours, and many of these have actually been seen by telescopes that watch in tenth rays and infrared light. These quick bursts are like sparks from a campfire, brief, bright, and unpredictable. The usual culprit is magnetic fields near the black hole that twist and suddenly snap back into new shapes, releasing energy, kind of like a stretched rubber band that suddenly pops and slings a bit of energy into the surroundings. Telescopes catch these as short flares, and because they come and go so quickly, astronomers watch constantly, like a night guard listening for the occasional alarm bell. A step up from those quick sparks are longer eruptions that can last weeks to years, depending on how much material gets involved. Picture pouring a bit of grease into a sink. Sometimes nothing obvious happens, but toss in a handful of hair and suddenly the flow gets messy for a while. In the galactic center, the hair might be a dense clump of gas or a stream from a passing star that gets captured and slowly drips onto the black hole. These mid-length events brighten the region for extended periods and can change the pattern of light across radio, infrared, and tenth-ray wavelengths. They're not permanent, but they're substantial enough that observatories around the world coordinate follow-ups to see how the black hole's environment responds. Rarer still are the dramatic, headline-grabbing disruptions when a star or a very large chunk of gas ventures too close and is torn apart over months to years. Think of stretching taffy until it pulls apart. Tidal forces from the black hole stretch and shred the object, and the shredded material forms a temporary feast that lights up the area. These tidal disruption events produce a strong, multi-wavelength glow that can outshine the usual background for a long stretch. Astronomers spot similar events in other galaxies and use them as labs to study how black holes digest matter, though in our own galaxy such full-on feedings are expected to be rare. On much longer scales, thousands to millions of years, the center of the galaxy can enter an extended active phase if it gets a steady supply of gas, like a stove left on low for a long time. The overall brightness and activity level can drift upward or downward over these grand intervals as the supply of fuel changes. These slow changes are the reason some galaxies look like fireworks for long stretches while others appear calm. The black hole's mood is tied to how much material is available. For human timescales this is essentially permanent, but in cosmic terms it's a temporary chapter. All of these behaviors, quick flares, medium eruptions, massive disruptions, and long-term swings, act like a set of cosmic hiccups, each with its own rhythm and warning signs. Observers use different instruments to catch each kind, fast instruments for the minute-scale flickers and long-term monitoring programs for the slow shifts. The good news for us is that even the most active episodes at the center of the Milky Way are unlikely to harm Earth because the black hole is very far away. The bad news for astronomers is that sometimes it's frustratingly unpredictable, like a cat that decides to vomit on the carpet at 2 a.m., messy, inconvenient, and impossible not to pay attention to. How bright could SGRA get compared to quasars? The black hole in our galaxy weighs in at about 4 million times the mass of the Sun, which gives a rough idea of how much fuel it could burn if fed. Brightness for a black hole comes from how much gas and dust it swallows and how efficiently that material converts into light. Think of it like cooking. A huge pot of soup will give off more steam than a cup, and the stove's heat setting matters too. If Sagittarius A** started gulping down a lot of gas, it would glow much more than it does now. Currently it's a very faint source by cosmic standards, more like a dim porch light. Quasars, on the other hand, are cosmic floodlights that outshine their whole galaxies. Those are the stadium floodlights of the universe. For SGRA** to reach quasar levels it would need a sustained, heavy meal of matter and to convert that meal into light efficiently. Short snack. A brief flare. A long buffet. A serious glow. There's a natural limit to how bright a black hole can shine set by a tug-of-war between gravity pulling matter in and radiation pushing it out. In plain terms, shove too much stuff in and the light it makes pushes the rest away. Picture filling a bathtub while someone cranks up a fan that blows the water back out. The balance point determines the maximum steady brightness. Less mass means a lower ceiling compared to the most monstrous quasars that sit in much heavier black holes. Even if SGRA** became very active, it would probably still be modest next to the brightest quasars. Those top-tier quasars live in much heavier black holes and eat constantly at a voracious rate. They are the skyscraper skyline seen from space. SGRA** could match the weaker end of active black holes or look like a nearby active galaxy, but it would be unlikely to rival the cosmic heavyweights that appear as beacons across the observable universe. Picture a city skyline replacing your porch light, impressive, but not the brightest metropolis you can imagine. From a practical point of view, telescopes would notice a dramatic change long before your eyes could. Instruments that see 10th rays and radio waves would light up like a constellation of cameras at a sports match. Our night sky would not suddenly be ruined for stargazers, though. The effect on Earth would be mostly an astronomical spectacle rather than a blinding event. We'd get great data, and astronomers would feel like kids in a candy store. And yes, scientists would probably throw a small party, quietly, because observatories. Everyday comparisons help. If a quasar is a roaring bonfire that can be seen across a field, SGRA** going active would be more like lighting the whole campsite. Still dramatic. Still exciting. But not the sort of light you'd use for tanning on the roof. Direction matters. Why beam orientation changes the story. Sagittarius A** sits at the center of our galaxy and, while usually calm, it can become active and shoot out narrow streams of energy and particles. These streams, often called jets, are not like a light bulb that glows the same in all directions. They are more like two powerful flashlights stuck on either end of a spinning top, shining intensely along specific lines. Because the energy is concentrated into tight beams, where those beams point changes everything. from whether nearby gas clouds get blown away to whether anything in our corner of the galaxy notices at all. Jets are made of fast-moving particles and high-energy light. When those particles race outward at speeds close to that of light, their emission gets focused forward, a bit like how raindrops in a fast-moving car fling forward more than to the sides. This focusing, called beaming, means a spot directly in the jet's path can receive a huge dose of radiation, while areas just off to the side get far less. Think of a garden hose with a nozzle set to a narrow jet. The person standing in front gets soaked, but someone a foot away stays dry. The same basic idea applies, except with 10th rays, gamma rays, and a lot more pinch-your-nose drama. If a Sagittarius A** jet were to aim in our direction, the effects would be the strongest we could imagine from that kind of source at a distance. High-energy light can ionize the upper atmosphere, scrambling radio signals and affecting satellite electronics, similar to what happens during big solar storms, though possibly stronger along the beam. Astronauts and people in high-altitude flights would face increased radiation exposure because our protective blanket of air and magnetic field works best against diffuse sources. A focused blast can punch through more effectively. Communication blackouts, damaged satellites, and brighter-than-usual auroras at unexpected latitudes could follow. It's not an apocalypse scene from a movie, but it would be a serious space weather event, like getting a cosmic espresso shot when you were expecting decaf. If the jet points anywhere else, life here would mostly carry on without fanfare. The galaxy, however, would not be so indifferent. Regions along the beam could see gas heated, stars' nurseries disrupted, and magnetic fields rearranged, which in turn affects how stars form in those neighborhoods. The orientation also controls which distant objects light up for observers. Astrophysicists get excited when a beam lines up with Earth because it makes the black hole appear much brighter and easier to study. In practical terms, whether Earth notices depends on geometry more than raw power. A highly energetic beam aimed elsewhere can wreak local havoc near the galactic center while we sip our coffee in peace. On a human level, orientation is the cosmic equivalent of standing behind a loudspeaker or off to the side. Preparing for the small chance of an on-axis event means better monitoring of the galactic center and hardening satellites and power grids against strong bursts of radiation. Simple everyday analogies help. You'd wear earplugs if you had to stand in front of that speaker, and engineers can design electronics to tolerate a little more cosmic noise. No need to move to another galaxy, but a little caution and good monitoring make all the difference when beams decide where to point. Local neighborhood effects in the galactic center. The center of our galaxy is a crowded neighborhood, and if the central black hole woke up, that neighborhood would feel it fast. Bright bursts of high-energy light, 10th rays and ultraviolet, would wash over the surrounding gas and dust, heating it and making clouds that were once dark start to glow. Think of it like turning a kitchen torch on in a foggy room. The tiny droplets pick up the light and you suddenly notice shapes you couldn't see before. Nearby gas clouds would warm, change color in infrared light, and produce strong emission that telescopes would spot as a sudden brightening. Gas motion would change too. Powerful winds and narrow beams of particles might push on clouds, compressing some and shredding others. When a wind slams into a cloud, it can act like a press, squeezing parts of the cloud so much they collapse and form new stars, or it can blow pieces away so nothing forms at all. Picture a gardener using a leaf blower on a pile of leaves. Some clumps get tighter and others scatter. This push and pull means star formation in the central region could go up in some pockets and drop in others, all depending on how the energy hits. Stars already living close to the center would notice the difference. Young stars with puffy gas disks, the places where planets grow, could have those disks evaporated by intense radiation, halting planet formation. Older stars might have outer layers heated and puffed up, losing mass faster than before. There's also the risk to small gas clouds and dusty clumps. The black hole's flare might rip them apart in a dramatic display, sending shock waves through the neighborhood. In street terms, it's like a sudden festival of fireworks, pretty to watch from a distance, but messy for anyone trying to keep a tidy yard. Chemistry would be altered as well. High-energy photons and energetic particles strip electrons from atoms and molecules, a process that changes the kinds of molecules that can exist. Complex organic molecules that survive in cool, dark clouds could be destroyed or transformed, while simpler ions and radicals increase. An everyday analogy is sunlight bleaching a colorful shirt. Some dyes fade while others barely change. For observers, this chemical makeover produces different spectral fingerprints, giving astronomers clues about how violent the episode was. Gravitational effects and stellar orbits would show subtle changes, too. Stars on very close orbits could be nudged by sudden mass flows or by the recoil of the black hole during powerful events, altering their paths slightly. That's similar to a crowded ice rink when a skater suddenly pushes through, nearby skaters adjust their lines. Although most stars farther out would keep their orbits, the innermost cluster would behave more erratically, with some stars possibly thrown into more elongated paths or moved inward where they face stronger tidal stretching. Local magnetism and cosmic ray levels would rise, producing more radio and gamma ray emission from the region and changing the way charged particles travel. This can affect how quickly clumps cool and how intact tiny dust grains remain. To borrow a household image, it's a bit like switching on a powerful magnet near a box of paper clips. Some get pulled together, others fling away. Overall, the galactic center's immediate neighborhood would be a place of competing processes, destruction and creation, calm and chaos, all happening on a scale far beyond anything our solar system would feel but fascinating for the nearby stars and clouds. Could the solar system feel anything from SGRA? Sagittarius A*, the supermassive black hole at the center of our galaxy, sits roughly 26.0 light-years away from the Sun. That distance matters more than people realize. Light and radiation from anything happening there take many thousands of years to get here. In plain terms, if the black hole flared up right now, we wouldn't feel it for a very long time. Think of it as a distant lighthouse whose beam is only now leaving the glassmaker's hands. Gravity from that black hole has almost no direct pull on planets in our system. The Sun dominates our local neighborhood like a big, nearby campfire. The black hole is a bonfire thousands of fields away. The pull you feel from your phone vibrating in your pocket is stronger for you than SGRA's tug on Earth's orbit. So no, the planets won't be yanked into new paths or sent spiraling out of the solar system by a sudden tantrum from the galactic center. Radiation is the more relevant pathway for impact, but even there the effect would be tiny. When a black hole becomes active, it heats up gas and dust as they fall in, producing bright light across many wavelengths, including 10th rays and gamma rays, which are just extremely energetic forms of light. By the time that high-energy light spreads across tens of thousands of light-years, it is smeared out and weakened. A flare from the center would register on our 10th ray and gamma ray observatories before it did anything else. In human terms, your backyard flashlight won't rival the sun spotlight on an airplane miles overhead, and detectors in space would notice the flash long before people on the ground would feel anything. Charged particles are another story that sounds scarier than it is. A powerful outburst can throw off cosmic rays, high-speed particles, but those particles don't travel in straight lines the way light does. The galaxy is threaded with magnetic fields that twist and scatter charged particles, turning any neat beam into a diffuse drizzle. It's like trying to send a focus spray through a windy field. By the time it arrives somewhere else it's dispersed. So even if the center shot out a stream of particles, Earth would experience only a tiny change in the background particle flux, nothing like a sudden radiation storm. There are extreme scenarios that would matter, but they require the black hole to be absurdly brighter than anything astronomers normally expect. If SGRA** somehow produced a focused jet aimed exactly at Earth and held that intensity for a long time, our upper atmosphere could see increased ionization, more charged particles up high, and sensitive satellites might need to be put into safe mode. That's a lot of ifs. In everyday language, the odds of that jet being perfectly pointed at us are astronomically small, and the usual activity is nowhere near threatening. Practical effects would start with instruments, not people. Space telescopes and radio observatories around the world would register changes first, giving scientists data to chew on. Some satellites might record a small uptick in background 10th rays, and long-term monitoring of the galaxy's center would note the flare. Your smartphone, barbecue, and hairdryer would remain blissfully ignorant. A little humor: your Aurora app might get jealous, but your weather app won't call it a storm. In short, an active phase of the galactic center is interesting and important for astrophysics, and it would be visible to our instruments across the electromagnetic spectrum. For the solar system itself, planets, atmospheres, and people, the effects would be negligible under normal active episodes. Only a wildly improbable, extremely powerful, and precisely aimed event would push conditions on Earth into anything worth worrying about. Cosmic rays and particle storms reaching Earth. An active supermassive black hole at the Milky Way's center would behave like a vast particle accelerator, flinging charged particles, mostly protons and heavier bits of atoms, into the galaxy. Those particles do not travel in straight lines like light, instead they scatter through magnetic fields in space, wandering for a long time before any arrive near Earth. The result would likely be a raised background of high-energy particles reaching our neighborhood of the galaxy, delivered more like a slow drizzle than a single, dramatic downpour. When those energetic particles reach the vicinity of Earth, our magnetic field and thick air act like layers of armor. Low-energy charged particles are largely deflected by the magnetosphere. High-energy ones can punch through that shield and slam into air molecules, sparking cascades of secondary particles, muons, neutrons and electrons, that shower downward. Those secondary particles are what ground detectors actually see, and they are the reason even people on the surface can feel a subtle increase in radiation during strong particle events. Think of it as a microscopic hailstorm that mostly bounces off the roof but occasionally sneaks through a skylight. People and machines respond differently to that extra particle traffic. For humans on the ground, the atmosphere gives very good protection, but airline crews and frequent flyers at high altitudes get a bigger slice of the radiation pie because the atmosphere is thinner up there. Astronauts are in a worse position. Without Earth's air and magnetic blanket, they would be exposed directly and would need stronger shielding or to shelter in more protected parts of a spacecraft. Long-term increases in particle flux can raise the cumulative radiation dose for those groups, which over years becomes a real health consideration, not immediate doom, but a steady nudge in risk that mission planners and medical officers take seriously. Not exactly the kind of rays you want for a beach holiday. Electronics take damage in their own way. Energetic particles can flip bits in memory, corrupt files, and cause transient malfunctions called single-event upsets. Satellites carry sensitive instruments and small computers, so a spike in particle hits can cause temporary outages, sensor errors, or the need for reboots. Navigation signals and radio communications, especially at high latitudes, can become unreliable when the upper atmosphere becomes more ionized. Power grids are more threatened by geomagnetic currents driven by big solar storms than by cosmic rays, but increased charging on satellite surfaces and sudden electronic errors could still create operational headaches. Imagine your satellite acting like it had a bad day after being pelted by invisible pebbles, annoying and expensive. Monitoring and mitigation are practical and familiar. Networks of particle detectors on the ground and instruments in space keep watch for rising particle levels so operators can switch satellites into safe modes, reroute high-altitude flights, and delay sensitive operations. Engineers design spacecraft and critical electronics with shielding and error-correcting systems to shrug off occasional bit flips. For people on Earth, ordinary life would mostly carry on. For airlines, astronauts, and satellite operators, the playbook changes a little: reroute, shield, and back up. Little humor helps. You won't need an umbrella, but you might want a firmware update. Atmosphere, climate and life under increased radiation. The black hole at the center of our galaxy can, when fed by gas and dust, light up and send a stream of very energetic radiation out into space. This kind of radiation includes 10th rays, gamma rays and high-speed particles called cosmic rays. Think of them as extremely energetic sunlight and a hailstorm of tiny bullets. When those high-energy visitors hit Earth's atmosphere, they slam into air molecules, knocking electrons free and creating a cascade of new particles and chemical reactions. The upper air acts like a shield and takes the first hit, but that shield can be changed, and a changed shield means changed sunlight at the surface. One of the clearest ways the atmosphere would respond is by chemical scrambling. High-energy photons and particles break stable molecules such as oxygen and nitrogen apart. That creates reactive compounds, especially forms of nitrogen that are very good at destroying ozone, the layer that soaks up the sun's ultraviolet light. Ozone is basically Earth's sunscreen. If that sunscreen thins, more ultraviolet reaches the ground. Short-term effects would feel familiar: stronger sunburns, more eye damage, and stress on plants. A coral or plankton bloom exposed to higher UV is like a toddler left out too long in the sun, badly stressed and less likely to thrive. Heating changes would also ripple through the atmosphere. Energy deposited high up makes the upper layers expand and warm, which can nudge wind patterns and the paths of jet streams far below. Those shifts can change where rain falls and how strong storms become. Sometimes the impact is subtle and shows up as a few chillier seasons in one place and drought the next year elsewhere. Sometimes it is blunt. For example, altered stratospheric temperatures can tilt atmospheric circulation and affect agriculture over large regions. The overall climate won't flip overnight from a single flare unless it's wildly enormous, but repeated or prolonged activity could push regional climates in noticeable ways. Living things respond in predictable and surprising ways. Plants are on the front line because they sit still and depend directly on sunlight. Increased UV can damage the tiny machinery in leaves that captures light, lowering crop yields and weakening wild plants. Marine life that depends on tiny organisms near the surface, phytoplankton, would be vulnerable, and that would ripple up to fish and seals. Animals that live at altitude or near the surface, like mountain goats or beach birds, would face higher exposure than forest-dwelling species. Humans would see practical impacts too. Airline crews and frequent flyers receive more radiation at cruising altitudes, electronics in satellites could suffer glitches from increased charged particles, and outdoor work would require better sun protection. Sunscreen and hats help, but microbes and crops don't carry SPF bottles. Some species would adapt, others would relocate, and some would decline. Microbes with fast life cycles could evolve resistance quicker than elephants. Ecosystems might reorganize around hardier species, and food webs could shift in ways that are hard to predict. People would also adapt by engineering fixes: hardened satellite casings, deeper-rooted crops, UV-filtering greenhouses, and better monitoring of radiation levels. Simple everyday steps, like timing outdoor work for lower UV periods or improving water and food storage, would matter for resilience. A touch of humor here: plants can't put on sunglasses, but we can build greenhouses that act like giant pairs of shades. Uncertainty would be the constant companion. The exact chain from increased radiation to a hungry polar bear or a failed harvest is complex because atmosphere chemistry, weather systems, and living communities interact in many ways. What scientists do know is straightforward: more high-energy radiation means more chemical change in the air, more energetic particles reaching lower altitudes, and greater stress on life that depends on current levels of sunlight and protection. Practical preparation, monitoring, and quick response reduce harm. In short, the atmosphere would take the first knocks, climate patterns could shift, and life would scramble to cope, with humans using technology and common sense to soften the blow. Oort cloud perturbations and comet delivery scenarios. The distant shell of icy leftovers around the Sun lies at enormous distances, thousands to tens of thousands of times farther from us than Earth, so it mostly notices local nudges like passing stars or clouds of gas. Those local nudges are the usual ways comets get knocked loose and sent inward. A nearby star's gravity gives a slight push, the gentle gravity of the whole galaxy slowly stretches or compresses orbits. That's called the galactic tide, which is just a slow, big pull, or encounters with dense knots of interstellar gas shake things up. Think of the Oort cloud as a jar of marbles on a porch. A friend stepping on the porch will rattle them much more than a distant thunderstorm. Short pushes, strong effects. At the same time, an active galactic center would mainly announce itself with light, fast particles, and winds rather than a direct shove. Radiation and cosmic rays travel across space at near light speed, so their arrival would be quick compared with the time it takes an Oort cloud comet to drift inward. Those high-energy visitors can alter comet surfaces, darkening them, breaking molecular bonds, or releasing trapped gases, which is more like microwaving the outside of an ice cube than tipping the jar. In everyday terms, sunlight can melt the outside of an ice cube, making it leak earlier than expected, but it won't roll the cube across the kitchen counter. Comets might become more fragile or start shedding material sooner when they finally get warmed by the sun, but their long, distant orbits won't be instantly rerouted by photons. Direct gravitational effects from the galactic center are extremely small at our distance. The central black hole and its immediate surroundings are far away relative to the scale of the galaxy, roughly 26,000 light-years distant, and turning on a bright central engine doesn't significantly change the overall gravitational layout felt out where the Oort cloud sits. So the most straightforward comet delivery scenarios driven by an active center are not gravitational in nature. Instead, indirect pathways matter more. Shock fronts and winds from a powerful galactic outburst can sweep through interstellar gas, potentially nudging nearby clouds and altering the environment around stars. If such a wave were to compress a local cloud of gas that our sun is moving through, it could slowly change the tiny gravitational tugs acting on distant comets. That's a multi-step, long-term chain of events. It's like a distant construction crew shaking the ground so faintly that only after months of tiny tremors do you notice a picture frame leaning differently. There are a few scenarios worth keeping separate. One is the minimal case. Increased radiation and particles hit the solar system but do little to orbital paths. Comets remain on their slow trajectories, though they may show more surface activity when they come in. A second, intermediate case involves environmental change in the sun's neighborhood, where shocks or winds from the center push on interstellar clouds, and those clouds in turn change the slow gravitational forces acting on the Oort cloud, gradually increasing the number of comets nudged inward. That takes a long time and a chain of cause and effect, so you wouldn't see a sudden rain of comets next week. A third, far less likely case would require an unusually strong interaction that rearranges large-scale mass near the sun, something that, given what we know about distances and mass distributions, is not considered a likely outcome. Think of it as the difference between a fireworks show viewed from miles away, pretty light, distant spectacle, versus someone standing in your living room shaking your jar of marbles. Timing is often the punchline in these stories. Even if a disturbance were effective at knocking comets loose, objects from the outer Oort cloud take very long journeys to reach the inner solar system, sometimes thousands to millions of years. So a change at the galactic center would likely be recorded in comet influx many generations later. Short-term changes, on the other hand, would be mostly about chemistry and surface behavior, comets becoming dustier, developing weak tails earlier, or fragmenting more readily as their volatile ices react to extra radiation and energetic particles. In plain talk, they might throw a little tantrum sooner, but they won't teleport to the inner solar system overnight. Practical examples help make this less abstract. When a freezer door is left open a crack, the surface of ice frosts, and tiny pieces flake off earlier than if it were tightly shut. Similarly, extra cosmic rays or tenth rays can make a comet's crust crumble a bit before it is warmed by the sun. A passing truck vibrating a porch might shift a jar only slightly. A gale-force wind would be needed to scatter the marbles widely. In galactic terms, nearby stars and clouds are the truck and the gale. An active center tends to be more like a loudspeaker across town. Funny, but reassuring, from the Oort cloud's point of view, the galaxy's fireworks put on a good show, but they don't usually reach across the parking lot hard enough to toss the marbles around. Star formation near the center, destruction or creation? The central region of our galaxy already holds thick clouds of gas and a few clusters of young, massive stars that tell a star birth can happen even in a crowded, chaotic neighborhood. Some of those clusters, like the arches and quintuplet groups, sit relatively close to the center and show that dense clouds there have collapsed into stars in the past. In other galaxies where the central black hole is active, astronomers sometimes see bright rings or pockets of fresh star formation sitting near, but not always right next to, the active core. If the black hole suddenly turned on and began blasting out intense light and fast winds, the simplest effect would be heating and clearing of gas. Hot radiation acts like a blowtorch on a damp sponge. It evaporates and pushes gas away, making it harder for clouds to cool and collapse into new stars. Short sentence for emphasis. Radiation pressure can literally shove material out of the central zone, so regions that were just starting to form stars might be stripped bare before they finish. Think of it as a garden hose that both waters and erodes. Sometimes the force of water helps seeds take root, but a blast will wash the soil away. Yet not all feedback is purely destructive. Fast outflows or jets plowing into a cloud can compress parts of it, and compression helps gravity win over pressure and start star formation. In some galaxies, astronomers have seen jet-driven knots of young stars where the jet hit a gas cloud. It's like stomping on a sponge and squeezing droplets out. In this case the squeeze can make a dense pocket collapse and form stars. So activation can be a double agent, killing some star nurseries while triggering others farther out or in sheltered pockets. Tidal forces very near a black hole are another factor. They stretch and tear apart loosely bound clumps of gas and small protostars. Close in, gravity from the black hole acts like a cosmic egg beater, and only the densest clumps survive. But farther away, where tides are weaker, the same events that clear out low-density gas can leave behind compressed shells and shocked fronts that fragment into new star-forming knots. The result is often a shift in where stars are born, fewer babies in the immediate center, more in a surrounding ring or scattered clumps. Real-world examples help make it intuitive. A wildfire clears undergrowth but can trigger sprouts in downwind areas where ash fertilizes the soil. Similarly, a central outburst might sterilize the inner region yet enrich and compress gas a little farther out and seed new growth. And a little humor helps. The black hole can be a terrible gardener. Sometimes it pulls up the seedlings and sometimes it plants new ones by accident. Overall, whether star formation is destroyed or created depends on balance, how bright the outburst is, how fast winds blow, the toughness of local clouds, and the geometry of jets and streams. The verdict is rarely all one thing. It's a messy, local story of both ruin and rebirth. Black hole feedback sculpting the Milky Way's shape. The center of our galaxy can switch from quiet to energetic, and when it does the outflowing energy acts like a sculptor working with gas instead of clay. Black hole feedback is simply the name for the ways energy and fast particles coming from the central dark object push, heat, or clear away the gas and dust that normally make new stars. We have already seen signs of this kind of activity. Huge lobes of energetic particles stretch well above and below the galactic plane, clear signs that the center has blown material outward in the past. Think of those lobes like giant smoke rings blown from a fog machine at a concert, only much larger and less polite. When the black hole feeds, matter falling in releases bursts of light, streams, and winds that shove on surrounding gas. These winds are not gentle. They can heat cold gas until it's too hot and diffuse to collapse into stars. A simple example from daily life is a leaf blower sweeping leaves off a lawn. The blower doesn't destroy the leaves, it just moves them and makes the lawn look different. In the galaxy this means the inner regions can become star-poor, because the raw materials for making new suns get kicked to the curb or spread out into a halo. Jets and winds also carve shapes in the disk of the galaxy. Narrow jets act like a pair of chisels that drill channels through gas, while broader outflows puff up the central layers, making the middle thicker and fuzzier. Picture a gardener pruning a shrub, cut in the right places and the overall shape of the plant changes. In the Milky Way, repeated energetic episodes from the center can erase or blur spiral features near the core, form central cavities or rings where gas was swept away, and deposit material into the halo. The magnetic field and fast particles carried by the outflow twist and tangle the gas further, like stirring cream into coffee and changing the pattern of the swirls. This feedback doesn't simply flatten or destroy the galaxy, it reshapes it over time and in distinct ways. Some gas can cool and rain back down later, fueling star formation at larger radii, so the change can be both destructive and creative. Observers look for signatures such as shock-heated gas, regions with very few young stars, and the glowing bubbles above and below the plane to read the black hole's handiwork. It's a slow-motion remodeling project on a galactic scale, less instant demolition, more ongoing redecorating, and the black hole plays the role of an occasionally dramatic, somewhat eccentric interior designer. Interstellar medium chemistry under intense radiation. The gas and dust between stars react in dramatic, but predictable, ways when flooded by very strong ultraviolet and 10th-ray light. That light is energetic enough to knock electrons off atoms and molecules, a process called ionization, which is simply the loss of an electron from a neutral particle. 10th rays punch much deeper into a cloud than ultraviolet does, so they change chemistry not just on the surface but throughout thicker clumps. Think of ultraviolet like sunburning rays that affect only the top layer of skin, while 10th rays are more like a doctor's imaging beam that sees and alters things deeper inside. Electrons freed by radiation turn quiet, slow chemistry into a noisy, reactive scene. Charged particles react differently than neutral ones. Some molecules fall apart quickly, while new, simpler charged species appear and participate in fast reactions. Molecular hydrogen, H2, the most common molecule, can survive surprisingly well because many H2 molecules together block the destructive photons, a self-protection trick called self-shielding. Carbon monoxide, CO, often used by astronomers as a stand-in to find molecular gas, is much easier to destroy by strong radiation, so CO can disappear even when lots of H2 remain. It's like seeing blank pavement after a rainstorm even though the soil underneath is still wet. Dust grains, tiny solid bits mixed with the gas, are both victims and helpers. On their cold surfaces complex molecules and ices form, analogous to frost building up on a car window overnight, but when intense radiation heats or erodes the grains those ices evaporate and dump new chemicals into the gas. Small soot-like molecules called PAHs, they're like microscopic barbecue smoke, glow in the infrared when excited, but under intense radiation they break apart. Charged grains also change how the gas behaves because they alter electric fields and stickiness. In short, the microscopic dust is the kitchen where many interstellar molecules are cooked, then sometimes flung back into the room. Secondary electrons produced when 10th rays and high-energy photons hit gas drive chains of reactions that would not happen in quiet space. These fast, low-energy electrons knock molecules into excited states, produce radicals, which are chemically aggressive fragments, and set off reaction cascades that build some species while destroying others. Complex organic molecules normally found in shielded cold pockets tend to be fragile and are either broken down or peeled off grain surfaces. Yet pockets that are shielded enough can still hide rich chemistry, so you get a patchwork, harsh chemistry near the radiation source, complex chemistry farther away. Kind of like neighborhood barbecue grills, some yards are singed, some keep their secret recipes. Observers detect these chemical shifts as changes in the gas's fingerprints. Some emission lines brighten, others fade, certain molecular tracers vanish while ionized species show up in abundance. Ions such as H3+ and molecular ions like HCO+ become more prominent in irradiated gas, while CO lines weaken relative to hydrogen. Astronomers use those clues to map where radiation is reshaping the chemistry. It's a practical tool, like smelling smoke to find a burnt toast, except here the smell is light at specific wavelengths that tells you which molecule survived the cosmic blowtorch. Overall, intense central radiation turns a sleepy interstellar cloud into a chemically active, ever-changing place where heating, ionization, and grain processing compete. Some molecules are resilient and hide behind shields, others are fragile and quickly vanish. The result is a complex but readable mix, and if you like a dash of irony, the same light that can sterilize molecules also helps astronomers read the chemical memoirs it writes in the gas. Visual spectacles, auroras and night sky changes. An outburst from the galaxy's central black hole would send a rush of energetic particles and extra radiation across the Milky Way, and when that shower meets Earth's magnetic shield those particles make the upper atmosphere glow. The magnetic shield is like an invisible bubble around the planet that steers charged bits toward the poles, where they smash into oxygen and nitrogen and cause light. Think of it as cosmic confetti hitting a ceiling and lighting up in different colors. Colors would change in ways people notice right away. Green, the classic northern light color, comes from oxygen a few dozen miles up and usually looks like rippling curtains. Higher up, oxygen can give off red hues, but that red is faint and high altitude, so you might catch it only if the display is intense. Nitrogen adds purples and deep blues. These are the colors that make the aurora look like a neon sign gone wild. In everyday terms, it's similar to how oil on water makes a rainbow sheen, except on a scale you can't fit into a puddle. Those curtains of light wouldn't be limited to the poles like usual. Mid-latitude cities could find green bands stretching over familiar skylines, and places that rarely see auroras might get a gentle wash of color on the horizon. On clear nights, constellations that people know by name could look as if someone has painted a soft veil over them. Faint stars disappear while the auroral glow steals the show. Long-exposure photographs would pick up much more detail than the eye, turning faint ripples into vivid waves, so your camera might outperform your memory and make your vacation photos look like sci-fi postcards. Nighttime would feel different even in suburbs. Streetlights would compete with strange sky glow, satellite streaks could be highlighted against the auroral backdrop, and meteor trails might be harder to spot when the sky itself is performing. Wildlife that navigates by stars or subtle darkness, moths, sea turtles, migrating birds, would notice the change, because bright, moving bands of color rewrite the usual night script. For stargazers and photographers, the advice is simple: step away from city lights, bring a tripod, and expect the sky to put on a show that's part science lesson, part disco party. Observational signatures for telescopes to chase. A sudden awakening of the black hole would first show up as bursts of 10th rays and infrared light, and those bursts are what 10th ray and IR telescopes should be chasing. 10th ray instruments like Chandra, XMM Newton and New Star would see quick, bright flares, the central region flickering on timescales as short as minutes to hours, because the innermost hot gas reacts almost instantly. That rapid flicker is like a car's high beams suddenly switching on and off while you're driving. It tells observers about the size of the emitting region and the rough speed of the gas. Simple measurements of how fast the brightness rises and falls are gold. Fast changes point to things happening very close to the black hole, whereas slow rises suggest the energy is being dumped farther out into the surroundings. In radio and millimeter wavelengths you'd watch for new structures and motion. Arrays such as ALMA and the VLA track the cooler, denser stuff farther from the horizon, and very long baseline interferometers like the Event Horizon Telescope can map details near the black hole's edge. A clear sign of activity would be a compact, bright knot peeling away from the center, a nascent jet, or a change in the silhouette the EHT normally sees. Polarization measurements, which tell you about magnetic fields, would likely increase or rotate. Think of polarization like polarized sunglasses for radio waves. The angle shifts when the magnetic field reorders. If the field flips or strengthens, the radio lights filter changes and our instruments can record that twist. Infrared observatories will pick up the warm dust and hot electrons dancing under the black hole's new mood. Facilities such as JWST and large ground telescopes can catch near-IR flares and broad emission lines from hydrogen and helium that get smeared out when gas is whipping around fast. Those broadened lines act like fingerprints stretched by motion. When the gas moves toward or away from us quickly, the spectral lines shift and widen, revealing velocity. The dust farther out responds more slowly, glowing like fog lit by a suddenly brighter lighthouse, a delayed infrared echo that maps distance and structure around the center. Look for light echoes and maser flashes in molecular clouds as a vivid, practical signature. Dense clouds near the center can light up when hit by a bright burst, producing reflected 10th rays, IR emission, or stimulated microwave lasers known as masers. Observing teams should monitor cloud complexes for sudden brightening. Catching an echo is like seeing sound reverberate off a wall, but with light over months to years instead of seconds. That delayed response lets astronomers reconstruct the three-dimensional layout around the black hole, a trick similar to using echoes to judge the size of a canyon. At the highest energies, gamma rays and even neutrinos may be produced if particles are accelerated to extreme velocities. Satellites like Fermi and ground-based Cherenkov telescopes would search for spikes in gamma-ray counts, while detectors such as IceCube would look for coincident neutrino events, those ghostly particles that hardly interact with anything. A correlated flash across 10th rays, gamma rays, and a neutrino detection would be like getting 3 different witnesses who all tell the same story. It points strongly to violent particle acceleration rather than simple heating of gas. Practical observing strategy matters. Continuous monitoring, rapid follow-ups, and coordinated multi-wavelength campaigns win the day. Quick response alerts to trigger-pointed observations during an 10th ray or IR flare allow VLBI snapshots, spectroscopic velocity measurements, polarization sequences, and high-energy searches to be taken almost at once. Archival searches for subtle brightening in molecular clouds or spectral changes provide context. Amateur radio monitoring and all-sky monitors can act as neighborhood watch, flagging unusual activity so the big facilities can swarm in. And yes, while the center of our galaxy isn't about to throw a rock through your window, the telescopes should be ready. A little cosmic drama makes for excellent science, and a tiny bit of black hole misbehavior is one of astronomy's best party tricks. What past activity tells us, relics in 10th ray and radio maps. 10th ray light seen coming from dense clouds near the center is like a stranded flashlight beam suddenly turning on across a foggy street. The clouds don't make the light themselves, they simply reflect a past burst from the black hole. Observers spot bright spots in those clouds that fade or brighten with time, and that variability is a clear sign the central source was brighter in the past. One well-known dense cloud near the center acts like a mirror that briefly glowed in 10th rays, and that glow carries the fingerprint of iron atoms, a distinctive 10th ray signature that tells astronomers the light was reflected rather than produced in place. That reflection trick is a powerful, simple clue. If a cloud lights up after the central engine had a flare, the cloud is echoing that flare, and we can use the echo to learn how intense the flash was and roughly when it happened. The 10th ray sky also shows towering, chimney-like structures and bubble-shaped cavities that seem to rise above and below the plane of the galaxy. Think of them as smoke plumes and hollowed-out rooms carved by a powerful wind or blast. These features are hot gas glowing in 10th rays, and their shapes point back toward the center, suggesting material was pushed out from there. Short flares make sharp, bright echoes, sustained winds or several eruptions carve larger, softer cavities. In plain terms, the 10th rays are the glowing smoke of a past tantrum by the black hole, messy, energetic, and telling. Radio maps bring a different set of relics into view, long, thin threads and broad lobes that don't show up in 10th rays. Those filaments line up like iron filings along an invisible magnet, revealing strong magnetic fields and streams of energetic particles. In the radio picture you can also spot lobes, balloon-like regions filled with charged particles streaming away from the center, that are basically the footprints of past jets or winds. Radio emission tends to persist longer than 10th rays, so these features act like fossil trails that record older, more extended episodes of activity. A tiny directed jet leaves a narrow radio trace, a sustained outflow inflates a larger lobe. It's like comparing a quick spark to a continuous garden hose, both wet the ground, but one leaves a different pattern. Putting the 10th ray and radio relics together gives a much richer story than either alone. 10th ray echoes pin down relatively recent, sharp flares and reveal which clouds caught the light. Radio structures map longer-lived outflows and magnetic routes along which particles were carried. By comparing where the 10th ray flashes hit and where the radio filaments point, astronomers can infer the direction and strength of past eruptions and whether the black hole fired off brief fireworks or a steadier stream. It is a bit like detective work. 10th rays show the fresh fingerprints, radio shows the footprints left in the mud, and together they let researchers reconstruct how active the galactic center has been. A little dramatic, yes, but also very helpful, and mildly satisfying for anyone who likes solving celestial mysteries. Numerical simulations and how they predict outbursts. Computer models let astronomers play out what might happen near a black hole, turning hard physics into something like a cosmic video game. These simulations mimic the flow of gas, the tug of gravity, and the push and twist of magnetic fields, all on a computer. Think of it like a weather forecast for space. You put in conditions, let the model run, and see whether you get a calm day or a storm. Short bursts of light called flares are one of the things scientists try to reproduce, because those are the fireworks that telescopes actually see. One common type of model mixes the rules for fluids and magnetic fields with Einstein's gravity. People call that GRMHD, which is just a mouthful meaning how magnetized gas behaves when space is very warped. In plain terms, the code tracks particles of gas as they swirl, heat up, and bump into each other under extreme gravity. Magnetic fields can store energy and suddenly release it. Picture stretched rubber bands snapping and releasing a small bit of chaos, and that release can light up the area in a bright flare. Observations in infrared and 10th rays provide examples of these flares, and simulations aim to reproduce their brightness and timing so researchers can test whether the underlying ideas are right. Models need starting assumptions, and changing those leads to very different results. If the incoming gas is steady, the simulations might show small, regular flickers. If a cloud of gas or a star's wind feeds more material, the computer can produce stronger, Messier outbursts. It's like baking, different ingredient amounts and oven settings give you a flatbread or a soufflé. Because we do not know every detail of the gas supply or magnetic setup near the black hole, scientists run many versions of the same scenario, an ensemble of runs, and look for patterns rather than a single exact prediction. So instead of saying, this exact second a flare will happen, simulations say things like, flares of this kind are likely when these conditions occur. Resolution and computing power limit what a model can show, and choices have to be made about which details to include. The simulation space is chopped into many small cells, like pixels in a photo, and smaller cells reveal finer structures such as tiny hot spots or narrow jets. Bigger computers, and clever numerical tricks, help capture those fine details. To check if a model is useful, researchers compare its output to real telescope signals, the timing of brightness changes, the color of light, and even the way light waves are polarized. When the simulated signals match observations, confidence grows. When they don't, that's science's polite way of saying back to the drawing board, often leading to new insights about magnetic fields, gas flows, or hidden feeding events that might trigger an outburst. Detecting warning signs with existing observatories. The center of our galaxy is already being watched with many kinds of eyes that see different kinds of light, and each one would pick up different warning signs if the big black hole woke up. Radio dishes like ALMA and the VLA listen to long-wavelength signals coming from hot gas and jets, while telescopes in space such as Chandra and New Star catch 10th rays that come from the hottest, most violent parts. Infrared instruments on the ground and in space, including adaptive optics systems on big telescopes and JWST-style imagers, can peer through the dust that hides the core in visible light. High-energy observatories such as Fermi and ground-based gamma-ray arrays look for extreme particles, and neutrino detectors like IceCube can sense ghostly particles that travel straight from the most energetic processes. Think of it as having a security system with microphones, thermal cameras, motion sensors, and a dog that barks when something really odd happens. A clear early sign would be a steady rise in brightness at several wavelengths, not just a one-off pop. 10th rays and infrared light would likely brighten as more gas falls inward and heats up. Astronomers would see a new baseline level rather than just isolated flares. Short, repeated flares would be another red flag. If the black hole goes from whispering to clearing its throat several times an hour, that's meaningful. Changes toward higher energy emission, meaning the light becomes dominated by more energetic 10th rays or gamma rays, would point to particles being accelerated to much higher speeds. And if radio telescopes suddenly show a jet or a knot of material moving away from the center, that's the classic sign of real activation, like spotting smoke from a chimney after smelling wood burning. Existing observatories are set up to catch these behaviors through continuous monitoring and quick reaction systems. Space 10th ray monitors scan the sky frequently and can trigger alerts, radio arrays run monitoring programs and can record rapid changes in structure. Interferometers like the EHT and ALMA can take very sharp snapshots to see small-scale features near the black hole. When one instrument notices something unusual, automated alerts and human networks allow others to point quickly and confirm the signal. It's similar to how a home alarm triggers the phone app, then neighbors check their cameras, and finally someone calls the fire department. Only astronomers trade push notifications and telescope time. There are limits and false alarms to watch for, so confirmation across different instruments matters a lot. Dust blocks visible light, so an optical telescope may see nothing while infrared and radio are full of action. Nearby objects, like variable stars or a passing cloud of gas, can mimic some signatures, and instrumental quirks sometimes produce fake flares. To reduce mistakes, teams look for coincident changes. An 10th ray flare matched by infrared brightening and radio structure changes is far more convincing. Even neutrinos or gamma rays arriving at the same time would be a smoking gun for particle acceleration, because those messengers are hard to fake. In practice, this means many observatories working together, sharing real-time data, and using simple cross-checks, like asking multiple witnesses if they saw the same thing, before declaring the center officially active. What new missions could learn from an awakening SGR-A? Sagittarius A** sits at the Milky Way center and, when it lights up, sends out flashes of 10th rays, infrared glow, and stronger radio waves that come and go on timescales of minutes to hours. New missions could watch those quick fireworks and learn how gas and magnetic fields behave right next to a black hole's edge, the region where gravity, light, and hot plasma tango in a crowded ballroom. By comparing fast 10th ray bursts with infrared flickers and radio hums, instruments can pin down where emission comes from, whether from a hot blob racing around the black hole or from shock fronts in an outflow, much like using several microphones at a concert to tell which speaker produced a sudden note. Next-generation high-cadence 10th ray monitors would be invaluable, because the brightest signals during an awakening are often in 10th rays. Short, continuous stares let scientists measure how quickly brightness rises and falls, which reveals the size and speed of the emitting region. Think of it like watching a kettle whistle. The speed of the whistle tells you how fast the water boils. Missions that combine high sensitivity with rapid readout could catch the faintest flares and the smallest fluctuations, teaching us about how matter piles up and then dumps onto the black hole. Adding an 10th ray polarimeter, a device that measures the orientation of light waves, would be like putting polarized sunglasses on the telescope. It tells observers how magnetic fields are arranged, because light gets polarized as it threads through ordered magnetic structures. Infrared interferometers and adaptive optics-equipped telescopes bring another layer of information, tracking hot gas and stars orbiting near the center and sometimes flaring in sync with 10th rays. High-resolution infrared measurements can follow hot spots, compact regions of heating that move around the black hole, which lets missions constrain orbital speeds and indirectly measure spin and gravity's stronger effects. An everyday analogy: tracking leaves swirling around a drain tells you about the drain's size and the water's speed. Coordinated campaigns that share data in real time, telescopes acting like a neighborhood watch with instant messaging, allow researchers to catch cause and effect. Did the infrared flare precede the 10th ray flash, or vice versa? That sequence clarifies which physical processes produce which colors of light. Submillimeter Very Long Baseline Interferometry, VLBI, upgrades and possible space VLBI elements would sharpen the silhouette of the innermost emission region and reveal structural changes as SGR-A* becomes active. Improving resolution is like switching from a cell phone photo to a high-end camera. Details emerge. Missions that add more telescope stations across the globe, or move receivers into orbit, can image motions and asymmetries in the flow, giving direct tests of theoretical models for how black holes accrete and launch outflows. Polarimetric imaging at these wavelengths would map magnetic field lines around the black hole. That's crucial because magnetic fields are the invisible ropes that can fling material outwards in jets or break rotation in disks. A coordinated multi-messenger strategy would broaden the lesson plan further. Neutrino observatories and high-energy particle detectors can look for coincident signals, if particles are accelerated to extreme energies during an awakening, those observatories might pick up signatures that electromagnetic telescopes miss. This is similar to noticing both the flash and the thud when a lightning bolt hits a tree. Light tells you where, while sound and other sensors tell you what else happened. Designing missions with fast alerts and automatic slews would let instruments respond quickly when SGRA* flares, maximizing the chance of catching rare, informative events. Finally, an active SGRA* would be a natural laboratory for testing computational models and refining mission designs themselves. Observing the same physical processes on a relatively nearby black hole helps validate simulations used to interpret distant, brighter nuclei in other galaxies. New missions could also trial technologies, distributed small satellites for persistent monitoring, rapid data sharing networks, or improved onboard processing to pick flares out of noise, which are useful beyond galactic center science. In short, an awakening SGRA* would teach new missions about extreme plasma physics, magnetic choreography, particle acceleration, and how to build nimble, multi-instrument observing systems. Plus, it would give engineers an excuse to design telescopes that react faster than today's coffee machine. Theoretical puzzles an active SGRA could solve. Sagittarius A** is the supermassive black hole at the center of the Milky Way, holding about 4 million times the mass of the Sun, and its occasional outbursts already hint that it has not always been so quiet. An active phase, when the black hole starts gobbling gas and spitting out energy, would act like a bright flashlight in a foggy room. We would suddenly see structures and reactions that are now too faint to notice. For example, the two enormous gamma-ray lobes known as the Fermi bubbles could be explained by past energetic episodes from that central engine. If SGRA flared up again, fresh energy could tie the smoking gun to the exact mechanics of how those lobes formed. That would answer whether the bubbles came from slow, steady winds or short, violent eruptions, the difference between a kitchen fan and a fire hose. A sudden turn-on would also teach us how black holes feed. Right now SGRA is an example of a low-feeding black hole, and astronomers debate how gas gets from the galaxy into the black hole's immediate neighborhood. Watching it wake up is like watching a slow cooker turn into a stovetop. You can learn which knobs to turn to change the cooking style. We would be able to see how gas heats up, how magnetic fields twist, and whether jets, narrow, fast streams of particles, are launched. Those observations would pin down theories about how material loses its sideways motion and falls in, something that sounds technical but is like watching shoppers funnel through a doorway. Do they line up or push through in a crowd? The galactic center also hides a mystery about missing pulsars and the weird mix of stars near the black hole. If SGRA became active, the resulting radiation and winds would interact with nearby stars and gas, revealing whether the black hole's moods sculpt the stellar neighborhood. In practice, a flare could strip gas from fragile objects or heat up clouds so they light up in radio and 10th rays. That would help explain why we see fewer spinning neutron stars than expected. It's a bit like turning on a leaf blower in a pile of leaves and then discovering which leaves were glued down and which were just waiting for a breeze. A lively center would be a natural laboratory for high-energy messengers. Active black holes can accelerate particles to extreme speeds and create gamma rays and neutrinos, the latter being ghost-like particles that normally pass through everything. If SGRA started producing these signals more strongly, scientists could finally test whether the galactic center contributes to the cosmic particles that experiments on Earth detect. Think of it as tracing the scent of a bakery back to a particular oven. Stronger, clearer emissions make it far easier to name the baker. That in turn would separate what is ordinary astrophysics from what might be signs of exotic physics, like dark matter, because one can only rule things out when the astrophysical foreground is known. Finally, a new active episode would let astronomers map the 3D structure of gas near the center in unusual ways. Bright flares act like sonar pings, their light bounces off clouds and returns as delayed echoes, revealing distances and densities. That technique has already given hints, but a sustained bright phase would flood the region with measurable echoes and let scientists build a detailed map, much as fog lit by a car's headlights reveals the contours of a road. Solving these puzzles would not only satisfy curiosity but also refine our broader picture of how galaxies breathe, grow, and sometimes throw tantrums. And yes, the universe has mood swings. SGRA might just be the drama queen we've been waiting to study up close. Risks to satellites, communications and space infrastructure. An active central black hole would send out extra bursts of high-energy light and fast particles that travel across the galaxy, and some of that could reach the solar system. Those fast particles, often called cosmic rays, are tiny bits of matter moving at enormous speeds. Picture microscopic hailstones pelting a satellite. When they hit sensitive electronics inside a spacecraft, they can flip a memory bit or fry a tiny transistor, causing a sudden glitch or a permanent failure. Everyday examples of this kind of trouble are the mysterious credit card errors or phone app crashes you get when a single strand of bad data corrupts a file. In space, the result can be a dead satellite or a spacecraft suddenly forgetting how to point itself. Communications would suffer in a few direct ways. The layer of charged gas high above Earth, the ionosphere, helps or hinders radio signals. Extra high-energy photons and particles increase the ionization there, and that can scatter or absorb radio waves so that GPS positions jump around like a bad streaming video. Pilots, ships, and anyone relying on precise timing for operations could see degraded accuracy. Banks and power grids that use satellite timing could get hiccups in synchronization. Satellite TV and internet links depend on clear, steady signals too, and increased noise or sudden outages would look a lot like a neighborhood outage after an electrician trips over a cable. Satellites themselves face physical wear and tear beyond sudden glitches. Solar panels and sensors slowly darken when blasted by energetic particles, which is similar to how a windshield gets pitted by tiny stones over time. The result is less power and poorer performance. Electronics accumulate damage from the total dose of radiation, like sunburn that eventually peels and leaves lasting harm, and delicate moving parts used to point satellites can fail if their control electronics misbehave. Surface charging is another issue. A satellite can build up an electric charge and then suddenly discharge in an arc that zaps circuits, akin to a tiny lightning strike inside a toaster, but far more expensive. The ripple effects on space infrastructure can be large and unpredictable. If many satellites in low orbit lose control or are disabled, they become drifting debris, and collisions can create more fragments in a domino effect that threatens other spacecraft. Think of it as glass shards spreading across a busy highway. Crewed platforms and missions would also be at risk. Astronauts would need to shelter behind thicker walls and spacewalks would be postponed, because even short bursts of high-energy particles raise cancer and acute illness risks. Large satellite constellations that provide communications and remote sensing services would be particularly vulnerable. Losing a chunk of them would mean spotty internet, delayed weather forecasting, and strained emergency services on the ground. In short, an energetic outburst at the galactic center would behave like a very bad storm for space hardware, knocking out some equipment instantly while quietly degrading other systems until they fail, and that cascade of problems can ripple down to everyday life here on Earth, just not as entertaining as a power outage during a cliffhanger TV show. Long-term risks to biospheres across the galaxy. Sagittarius A, the giant black hole at our galaxy's center, can act like a cosmic blowtorch if it becomes active, sending out intense light, high-energy particles, and fast winds that travel far beyond the center. That light includes 10th rays and ultraviolet rays, which are more energetic than ordinary sunlight and can punch through atmospheres and break chemical bonds. Think of it as changing a dim lamp into a welding torch aimed at the galaxy. The closer you are, the more you feel the heat. Planets hit by this extra radiation would face direct harm to living cells and to the air that protects them. High-energy particles and 10th rays can damage DNA, increasing cancer and birth defects in animals in the same way that heavy sunburns and radiation exposure do on Earth. On top of that, the chemistry of an atmosphere can be altered. Protective layers that block harmful ultraviolet light can be depleted, allowing much more ultraviolet to reach the surface. Remember how human-made chemicals once thinned Earth's ozone layer and let more UV through? This would be like that, but driven by space weather instead of bottles and aerosols. Microorganisms living under soil, under rocks, or in deep oceans would fare much better than surface life, because a few meters of water or rock is very good at stopping dangerous radiation. So while surface forests and shallow water ecosystems might die back, underground and deep-sea life could keep chugging along, like stubborn houseplants surviving a power outage in a basement. Long-term climate and atmospheric changes could slowly turn once habitable worlds into barren ones. Strong particle winds can strip away the upper layers of an atmosphere over long times, especially from smaller planets or moons that lack a strong magnetic field. Mars offers a real-world example. Solar wind has helped remove part of its atmosphere over time when the planet lost a global magnetic shield, leaving it thin and cold. If a galactic center turned active, similar processes could accelerate on vulnerable worlds, eventually drying them out and removing the insulation that keeps liquid water and life stable. When photosynthesis collapses because sunlight is blocked or the air chemistry is altered, whole food webs can follow. Tiny plankton dying leads to fish die-offs, which then affects birds and mammals. It's like removing the bottom of a Jenga tower, the rest can fall away over decades to millennia. Effects spread unevenly through the Milky Way. Regions close to the galactic core, where stars are crowded, would be the hardest hit and might see repeated bad weather episodes that make complex life rare or short-lived. Farther out, the impacts fade, but they don't vanish entirely. High-energy particles can travel long distances and change the chemistry of gas between stars, altering where and when new stars and planets can form. That matters because fewer new stars means fewer fresh worlds to host life in the future. Sometimes the outflows from an active core can even compress gas clouds and trigger star birth in other zones, which is the universe's odd way of both destroying and creating opportunity at the same time. Picture a wind that scatters seeds in one field and plants trees in the next. Evolutionary consequences are a mixed bag. Increased radiation raises mutation rates, which in microbes could accelerate adaptation and lead to rapid shifts in communities. Bacteria might evolve new tricks to cope, while complex life with long generation times would struggle more. Simple organisms, like lichens or deep microbes, have huge tolerance ranges and could become the long-term survivors, dominating landscapes after surface die-offs. Subsurface refuges, cave systems, deep ocean vents, or pockets under ice, would serve as life's bunkers. A little humor helps. Microbes would be the ultimate apocalypse roommates, quiet, hardy, and impossible to evict. Technological civilizations would face hard choices. Shielding habitats with thick layers of rock, living under ice, or creating artificial magnetic shields are ideas that work in principle, but they require long-term planning and resources. In any case, the risk is patchy. Some star systems could be sterilized or made inhospitable for long stretches, while others remain relatively safe havens. Over galaxy-spanning timescales, an active central black hole can reshape which regions are fertile for life and which become cosmic deserts, leaving a permanent imprint on the distribution of biospheres across the Milky Way. Human timelines versus black hole timelines, who wins? At the center of our galaxy sits Sagittarius A*, a supermassive black hole with a mass about 4 million times that of the Sun, and it's located roughly 26.0 light-years from Earth. Astronomers have seen signs that it has been more active in the past. There are giant lobes of energetic gas above and below the Milky Way that point to episodes when the center was speaking louder than it is now. That tells us two things right away. The black hole can change its behavior, and when it does, those changes unfold on scales much larger than everyday human life. People live in decades, build cities in decades, invent things in years. A single person's lifetime can see phones transform from bricks to computers in your pocket, and societies can rise and fall in a few centuries. Plant a sapling and it will be a respectable tree by the time your grandchildren are adults. These are fast, immediate rhythms we understand and can react to. The emergency alarm rings and you move. Humans operate on short, punchy timelines. Black holes keep a very different kind of clock. They're feeding cycles, when they gulp down gas and light up, and the structures they make around them evolve over time so long they feel almost frozen to us. Changes build up slowly, like a glacier carving a valley, rather than an earthquake cracking the pavement. When the central black hole of a galaxy becomes active, it can blow out winds or launch jets that shape the galaxy over ages. The process is patient, it lets the cosmos simmer rather than boil. Think of it as a slow cooker compared to our fast microwave lifestyles. The black hole has a patience that would make a monk jealous. So who wins? It depends on what winning means. In the short term, humans are the winners. If Sagittarius A** flared up tomorrow, the distance between us and the center makes immediate, catastrophic effects unlikely. Our planet wouldn't be instant toast from a galactic tantrum, the energy dissipates across vast space. Satellites might see increased radiation like a bad sunburn, and some sensitive instruments could be affected, but civilization wouldn't collapse just because the center hiccuped. We can build shields for electronics, reroute missions, and adapt our tech. We react fast. We can also spot warning signs because astronomers watch the sky continuously, like a neighborhood watch for cosmic mischief. Over long stretches, however, the black hole wins the endurance contest. Its episodes of activity sculpt the galaxy, influence where stars form, and can sweep gas out of whole regions. Over epochs, that changes the raw material available for new generations of stars and planets, and thus the stage on which life might arise. On galactic terms, humans are a very brief flare of activity. On human terms, the galaxy's win is so slow it barely registers. So practically speaking, in the here and now, humans are safe and adaptable, and we win by being quick and inventive. In the grand, slow-motion movie of the Milky Way, the black hole holds the director's chair. Survival strategies for science and society. An active galactic center would likely increase the amount of energetic light and charged particles reaching parts of the Milky Way, and that means both science teams and everyday communities need practical, down-to-earth plans. Reinforcing power and communication networks is a top priority, burying critical cables where feasible, adding surge protectors at key substations, and building local microgrids that can operate independently if long-distance transmission fails. A good example from daily life is how people use uninterruptible power supplies for computers. Scale that idea up so hospitals, water treatment plants, and satellite ground stations can keep running even if the main grid hiccups. Simple redundancy is powerful. Duplicate critical systems in different places so one event doesn't take everything down. Protecting satellites and instruments comes next, and the approaches are refreshingly straightforward. Space hardware can be built with tougher electronics and extra shielding, and operators can put craft into a safe mode that reduces damage during a burst. Ground-based observatories should develop remote and autonomous operation capabilities so telescopes can keep collecting data without people on site, much like security cameras that keep recording during a blackout. Data safety matters just as much. Keep multiple copies of important datasets in different countries and on media that don't require constant power, for example rugged drives stored in underground vaults or even printed copies of essential instructions. Yes, paper still has a role. Health, food, and water security finish the short list of immediate human needs, and practical steps are easy to picture. Buildings with thicker walls, basements, and water barriers reduce exposure to increased radiation or particle flux. Think of it as using your house like an umbrella when the weather turns weird. For crops, indoor farming with controlled lighting and UV filtering films protects plants from spikes in harmful radiation, and seed banks, kept in multiple safe locations, make sure we can replant quickly if outdoor agriculture is damaged. Hospitals and pharmacies should plan for supply chain interruptions by keeping essential medicines and spare equipment on hand, and by decentralizing storage so a single strike doesn't wipe out reserves. Science continuity requires both clever engineering and community planning. Distributed observatories across the globe, including small, inexpensive instruments in many countries, reduce the chance that a single event hides critical phenomena from researchers. Citizen science can help too. Trained volunteers with simple detectors or backyard telescopes can provide extra eyes and redundancy, similar to neighborhood watch programs but for the sky. Maintaining specialized equipment often needs cold storage or continuous cooling, reliable backup power and locally trained technicians, not just remote experts, will keep those systems alive, a bit like having your own mechanic for a prized old car. Society-wide preparedness is as much about communication and governance as it is about hardware. Clear, trustworthy public messaging prevents panic and counters rumors. Local authorities should run simple drills and provide straightforward checklists for families and businesses. International cooperation is essential since the effects wouldn't stop at borders. Shared monitoring networks and pre-agreed plans for data sharing speed up scientific understanding and emergency response. In short, combine durable infrastructure, distributed and redundant science systems, practical health and food backups, and good old-fashioned cooperation, and humanity stands a much better chance of keeping both laboratories and daily life humming, even if the galaxy decides to throw a tantrum. Science fiction becomes plausible, popular culture impacts. The center of our galaxy holds Sagittarius A*, a compact, extremely dense object that quietly sits at the heart of the Milky Way. If it began to light up and throw out bright bursts of energy, people would suddenly take science fiction stories a lot more seriously. Films and TV that once felt like wild imagination would be reread as plausible scenarios, and that changes how creators and audiences talk to each other. Popular shows and movies that leaned on careful science have already shown how much audiences appreciate realism. Interstellar hired a real physicist to make its black hole scenes believable, and The Martian won praise for showing the nitty-gritty of survival rather than miraculous fixes. Those examples become touchstones. Producers call in consultants, writers research actual space hazards, and viewers stop forgiving impossible tech on the grounds of a cool plot. Short attention spans still crave spectacle, but now spectacle with a believable foundation wins awards and water cooler debates. People who once loved flashy faster-than-light chases might find themselves more interested in dramas about how communities prepare for high-energy radiation or disrupted satellites. Books, games, and museums react fast. Publishers push realistic thrillers and survival guides that read like helpful manuals. Game designers build scenarios where players manage power grids, patch radiation leaks, or run a battered radio network between towns. Planetariums fill with updated shows explaining what an active galactic center does, using clear analogies like comparing a black hole's glowing gas to a whirlpool lit by torches. Local science centers get busier, families go for hands-on exhibits about shielding and communications. It becomes normal for a weekend outing to include a talk about particle showers and for kids to come home wanting to build a model radiation bunker with LED lights and duct tape. Everyday culture shifts in smaller, funnier ways too. Fashion picks up cosmic motifs, jackets with swirling, jet-like embroidery and jewelry that mimics the bright ring around a glowing object. Memes explode. Someone will make a viral tutorial on how to turn a toaster into a pretend observatory prop. Cosplayers start showing up with clever costumes that echo astrophysical themes. Think LED halos for accretion disks or clever use of smoke machines for jets. Even local theater troupes might stage black hole-inspired plays, and bar trivia nights get new categories about space weather and communication outages. Credibility in storytelling becomes valuable currency. Documentaries and limited series that take the time to explain the real risks, how high-energy light can scramble electronics or how charged particles can alter the sky, gain trust. That trust spills over into public conversation about policy and preparedness. People demand plain language explanations from experts. In the supermarket, the conversation at the checkout might shift from celebrity gossip to whether the family's emergency kit has a crank radio. It's a strange thing. Science fiction starts behaving more like a user manual, and culture adjusts by favoring stories that feel like they could teach you something useful, or at least make you laugh while you learn. The scientific goldmine, experiments you'd want to run. A sudden feeding frenzy at the galaxy's center would turn Sagittarius A into a bright, variable lighthouse across the whole spectrum, and the first experiments would be coordinated, fast-response monitoring from radio waves up to gamma rays. Telescopes that see different kinds of light would be trained on the source at the same time, because each band tells a different story, radio shows gas motion, infrared reveals warm dust and stars, 10th rays expose hot plasma, and gamma rays point to the most extreme particle accelerations. Think of it like watching a thunderstorm with a regular camera, an infrared camera, and a lightning detector all at once. You get a lot more about the storm than from any single view. Rapid, continuous light curves and spectra would let us measure how fast the source changes and what physical processes switch on or off during flares. Precision imaging with very long baseline interferometry would be a top priority to resolve the region just outside the event horizon, while near-infrared interferometers would track tiny motions close to the black hole. Combining radio dishes across the globe makes a telescope the size of Earth, which is basically like stitching together many tiny windows to make one giant eye. That lets us try to image the photon ring and moving bright spots, hot clumps of gas circling the black hole, and watch them shift and fade. Small orbits of those clumps would let us test how light bends and time stretches near a massive object. In plain terms, watching marbles race around a drain to learn the shape of the drain itself. Polarization measurements would go hand in hand with imaging, telling us the geometry and strength of magnetic fields. Picture iron filings showing the invisible pattern around a magnet, but on a galactic scale. High-energy particle experiments would aim to catch the black hole in the act of accelerating particles to extreme speeds. Neutrino observatories and cosmic ray detectors would be on alert during bright episodes, because a neutrino signal arriving with a flare would point to protons being smashed into gas or light, not just electrons. Neutrinos are like ghostly messengers that sail through everything, so detecting them from the center would be a smoking gun for hadronic processes. Gamma-ray and 10th-ray telescopes would search for clues about how particles gain energy, while laboratory plasma experiments and computer simulations would try to mimic the acceleration and jet-launching physics in scaled-down, controllable settings, like running a small tornado in a lab to understand a real one outside. Finally, experiments would probe how an active phase affects the neighborhood, molecular clouds, young stars, and the orbits of the so-called S-stars near the center. Spectroscopic mapping would measure gas speeds and chemical fingerprints to see if flares change cloud chemistry or trigger or suppress star formation. In everyday terms, it's like checking whether a campfire warms nearby marshmallows or burns them to a crisp. Long-term astrometric tracking of stars close to the black hole would test gravity under extreme conditions and could reveal any shifts in the black hole's mass or spin as it eats. Reverberation studies, measuring how different kinds of light echo after a burst, would act like sonar to map distances and structure of the region. Coordinated networks, quick alert systems, and even citizen science programs could all join the effort, because when the galaxy's central engine wakes up, every additional pair of eyes helps. Comparing Sagittarius A to other active galactic nuclei. At the heart of our galaxy sits a black hole that, by cosmic standards, is pretty shy. Active galactic nuclei, or AGN for short, are the show-offs of the universe, bright, noisy, and fed by a steady stream of gas and dust that falls in and heats up. Think of an AGN as a roaring bonfire at a backyard party. Sagittarius A, SGR A*, is more like a single candle on the porch. It can flare up for a short time, but it never reaches the continuous blaze seen in true AGN. Fuel supply matters more than size. Some galaxies funnel lots of gas into their centers through collisions or tightly wound spiral arms, and that steady diet turns their black holes into luminous AGN. Our Milky Way, on the other hand, provides only a trickle. Picture two kitchens, one with a full pantry and a cook making a feast, the other with a single loaf of bread and someone heating a snack. Both have stoves, but only one is running at full steam. Because SGR A* has little to eat, its surrounding gas never forms the bright, thin disk that lights up quasars and Seyfert galaxies. Jets provide a clear visual contrast. Many powerful AGN launch vast, straight jets of particles like fire hoses, visible across millions of light-years and lighting up radio telescopes. M87, for example, sports a dramatic jet you can almost imagine as a cosmic firework. Sagittarius A* shows no such large-scale jet. If it has any outflow, it's faint and local. In everyday terms, some black holes are industrial water cannons. SGRA** is a garden sprinkler that occasionally sputters. Observations across the spectrum highlight the differences too. Bright AGN glow strongly in ultraviolet and 10th rays because the infalling gas gets extremely hot, while SGRA** is relatively dim in those bands and is most easily studied in radio and infrared light. Short bursts of 10th rays pop up from SGRA** now and then, like random sparks from a dormant fireplace. Variability also behaves differently. Very active AGN can change over long, stretched-out times, whereas smaller, quieter systems can flicker more quickly. Mass plays a role, but it's not everything. A heavier black hole with little fuel will still be quiet, while a somewhat lighter one with a steady supply can outshine many neighbors. Host galaxy environment and recent history shape the outcome. Galaxies that have merged or that channel gas inward tend to light up their centers. The Milky Way's calmer life means SGRA** sits in a modest state compared to the blazingly active nuclei found in some other galaxies. So while Sagittarius A shares the same basic machinery as active galactic nuclei, a massive gravity well that can pull in matter and emit energy, the difference comes down to appetite and surroundings. One is a bustling kitchen, the other a cafe with the sign "Back in 5 minutes." Energy budgets. Could SGRA outshine the Milky Way? The maximum steady power a black hole can shine with comes from a simple rule: the outward push of light balances the inward pull of gravity. Called the Eddington limit, it scales with mass, and for a roughly 4 million sun central black hole comes out to the order of 10^44, 10^45 erg per second, which is the same ballpark as 100 billion suns added together. In everyday terms, that means the whole, if fed heavily and efficiently, could produce a total light output comparable to or a few times greater than the whole Milky Way's light. Put simply, the black hole's theoretical top-end brightness is not laughably small compared with the galaxy, it is large enough to compete. Turning mass into light is surprisingly efficient near a black hole. Gas falling toward the hole can heat and glow as it spirals in, converting a noticeable fraction, commonly around 10%, of the falling mass energy into radiation. That is vastly more efficient than burning fuel in a car engine. Converting matter to light at these efficiencies is like squeezing the energy of many fuel tanks into a single bright bulb. A tiny amount of matter, handled this way, can produce a luminosity comparable to billions of suns, so the question isn't whether the black hole can be bright, but whether it gets enough food. Current quietness aside, the key number to ask is what fraction of the Eddington limit the black hole reaches. If it sustained somewhere near the Eddington rate, it would outshine the galaxy in total output. If it only reached a few percent of Eddington, the black hole would still dominate the high-energy sky, 10th rays and ultraviolet, even while the galaxy's combined starlight remained brighter in visible and infrared. To match the Milky Way's full power across all wavelengths you'd need a significant fraction of the Eddington luminosity, on the order of tens of percent. Lower activity gives dominance in only selected bands, like a nightclub spotlight stealing attention from the city skyline. How the energy is delivered matters too. If most of the power is beamed away in narrow jets, then along those beams the black hole can appear enormously brighter than the rest of the galaxy, while other directions hardly notice, a spotlight versus a porch light. Dust and gas around the center will absorb some of the energetic light and re-emit it at infrared wavelengths, effectively redistributing the energy into the galaxy's glow. So the same total power can make the galaxy look very different depending on whether the black hole sprays energy in focus streams or bathes the region evenly. In practical terms, then, Sagittarius A** could outshine the Milky Way if it were fed enough material and converted that material into radiation at the efficiencies astrophysicists expect. It's like a quiet neighbor who, given a truckload of fireworks and a match, could easily become the brightest thing on the block, at least for a while, especially if the display is aimed right at you. Public reaction, media narratives and misinformation traps. An awakening at the galaxy's center would produce bursts of bright, high-energy light that telescopes would catch first, long before people on the ground felt anything unusual. Scientists would explain this in plain language: the black hole eating gas and dust heats that material until it shines, especially in 10th rays and radio waves, like a distant flare lighting up a fog. That simple picture helps calm fear, but it doesn't stop other forces at work: curiosity, rumor, and the way humans process dramatic news. Initial public reaction would be a patchwork: wonder in one corner and worry in another. Social feeds would overflow with screenshots of telescope images, striking visuals that are easy to share, and with them would come memes and jokes. Someone always posts a cat wearing sunglasses. But alongside humor, some people would genuinely worry about direct impacts. Will it fry satellites? Ruin the climate? The scientific consensus, relayed clearly, would matter here. Most experts would stress that Earth sits very far from the galactic center and that direct harm is unlikely. Clear, repeated explanations from trusted institutions can act like a calm friend at a noisy party. They help, but they are not a cure-all. News outlets would fall into predictable patterns. Serious reporting would bring astronomers on camera, show graphs and explain scales, and include experts who translate jargon into everyday terms. Other pieces would lean toward narrative drama. The Milky Way roars makes a better headline than astronomers observe increased activity, and headlines shape mood fast. Human interest angles would pop up too: profiles of the telescope teams, interviews with amateur stargazers, and even quirky local stories about people buying telescopes as if they were concert tickets. Balanced coverage that juxtaposes big visuals with simple explanations works best, because it gives context without boring readers. Misinformation traps would open wide, and they come in familiar shapes. Old images from unrelated events get reused and captioned misleadingly. A dramatic image of auroras or a solar flare might be repurposed and labeled as the galactic center erupting, and that's persuasive to someone scrolling quickly. Pseudo-experts and social accounts with large followings can amplify false claims, offering catchy but wrong takes such as, "This will alter gravity," or "Special supplements will protect you from galactic rays." Scams would follow too, people trying to sell dubious protection kits or fake insider reports. A good real-world example is how panic around storms sometimes spawns overpriced generators and fake charities. The pattern is similar here. Spotting and avoiding these traps is not hard if a few simple habits are followed. Check the source. Reputable space agencies and major observatories will publish primary data and plain language FAQs. Reverse image search can reveal whether a striking photo is actually from something else. Watch for sensational language. Words that promise secrets or absolute certainty are red flags. Finally, ask whether the claim would be reported by multiple independent scientific outlets. If not, treat it with skepticism. A little patience and a quick search can save a lot of worry and a bit of embarrassment. Journalists and scientists both have roles to play in shaping narratives. Reporters should resist the easy route of headlines that feed panic and instead pair dramatic visuals with straightforward context and explicit statements of risk. Scientists can help by using relatable analogies, likening the event to a campfire many miles away rather than a neighborhood blaze, and by proactively correcting misinterpretations. And the public can help too. Share confirmations from trusted organizations, not the flashiest post, and don't amplify claims that rely on fear. Humor helps. A well-timed joke about not needing a tinfoil hat eases tension, but clear facts do the real work in keeping people calm and informed. Policy, preparedness, and international coordination. The first practical step is building a single, trusted global warning chain that can move from telescope to town hall in minutes. Space agencies and observatories already share data when the sun acts up, but an event from the center of our galaxy would require wider reach and clearer handoffs. Think of it as a severe weather broadcast for outer space. Scientists detect unusual emissions, analysts translate those signals into likely impacts, and emergency managers issue actions people can actually follow. Agencies such as the UN office that deals with space activities, communications unions that manage radio spectrum, and national space weather centers would all need predefined roles so messages don't get lost in bureaucracy. National preparedness must focus on the systems people rely on every day: power, communications, transportation, banking, and emergency health services. Utilities can prepare by developing plans to isolate vulnerable transformers and by keeping spare parts and crews ready to move. Airlines already alter polar routes when charged particles increase. Similar playbooks could be adapted for broader disturbances to protect navigation and passenger safety. Hospitals and dialysis centers should have tested backup power and offline patient records. Banks and payment processors need contingency modes for clearing transactions if satellites or internet links degrade. Practical examples include rotating backups for critical data and pre-authorized emergency purchase orders so replacement equipment can cross borders without delays. International coordination would need to go beyond polite information exchange into binding arrangements for mutual aid and common thresholds for action. Existing space-related treaties provide a legal backbone, but they don't spell out day-to-day operational cooperation for extreme space events. Communication standards, who declares an alert level 1, 2, 3, and what each level actually means, must be agreed in advance. Joint exercises are essential, practicing responses between countries, private satellite operators, telecom carriers and financial clearing houses will reveal weak links. Think of it like international disaster drills for storms or pandemics, but with a focus on signals, spectrum, and satellites rather than ambulances and masks. Capacity building and equity deserve equal attention so that poorer countries and small operators aren't left scrambling. Many nations lack hardened infrastructure or the technical teams to interpret space alerts. Offering shared data portals, training workshops, and pre-positioned hardware can make a big difference. Low-cost measures, such as recommended operating procedures to switch satellites into a safe mode, or community-level advice to protect radios and power strips, can be lifesavers. Sharing expertise and resources is not charity, it's self-interest, because satellite failures and cascading outages anywhere can ripple through global finance, shipping, and communications. Policy instruments should balance speed with transparency. Emergency authorities will need legal authority to regulate spectrum, restrict flights, or mandate power rationing in extreme cases, but those powers must be tied to clear triggers and sunset clauses to avoid abuse. Public communication plans should be simple, avoid technical jargon, and include examples people can act upon, like saving important files to an external drive or unplugging sensitive electronics during a severe alert. Regular reviews and updated tabletop exercises, involving government, industry and civil society, keep plans sharp. And a bit of humor helps relieve tension. Plan well enough that when the cosmos throws a tantrum, we can respond like a team that practiced its drills, not like a group that just yelled, abort, and hoped for the best. Artistic and philosophical reflections on a woken giant. Sagittarius A** sits quietly at the heart of our galaxy most of the time, a massive object that usually only announces itself faintly through radio and infrared light. If it became active, that quiet center would flare, sending out bright bursts of radiation and streaming energy that could be visible across many kinds of telescopes. In plain terms, material falling into the giant gets very hot and lights up, and sometimes powerful jets shoot out like garden hoses of light. The physics is complex, but the visible result for artists and thinkers is dramatic and immediate. For people on Earth the risk of harm would be extremely small because it is very far away, yet the psychological impact could be enormous, like learning a familiar neighbor has been leading a secret life. Painters would lean into extreme contrasts, using deep, velvety blacks rimmed with sudden white or neon strokes to capture the idea of something immense becoming visible. Photographers might use long exposures and timed sequences to show the center brightening, or stitch together time-lapse panoramas of stars trembling in new light. A single flare could become the focal point of an entire series. Filmmakers could treat the activation as a soundtrack cue, a low, sustained note builds, then snaps into a chorus, and visual motifs, spiral, funnel, wake, repeat like a heartbeat. Sound artists already convert telescope readings into audible ranges, and those data-driven compositions would be perfect for immersive installations, a black hole's feed turned into a sound bath for gallery-goers who like their science with a side of ambience. It would be oddly tempting to make merch. People do that with thunderstorms, they'd do it with a galaxy's tantrum too. Philosophers and poets would return to old themes with fresh urgency: the sublime, the balance between awe and fear, and what it means to be a species that can both watch and interpret cosmic events. The awakening of a giant at the galaxy's center forces questions about scale, not only physical but moral, because it shows how tiny human projects are beside cosmic processes, yet how big our curiosity is in response. Everyday parallels help make that clear. When a city loses power, neighbors talk in doorways and priorities shift, and similar shifts in focus happen in quieter ways when stargazers get new light to study. Some thinkers would argue for humility, others for boldness. Both stances have real examples in civic life, like when communities balance heritage preservation with new development. The conversation would be lively. Expect metaphors involving sleeping animals and rumbling engines. And jokes. Short ones. Artists working with communities could translate the event into accessible experiences that blend science and ritual. Museums and planetariums would update shows, schools would create projects where students paint what the sky felt like the night the center flared, and street artists might project shifting halos onto building facades during public viewings. A practical example from everyday culture is how cities celebrate meteor showers with rooftop parties and hot chocolate. Similarly, communities might host night walks with guided telescope stations and poets reading on benches. Collaboration between scientists and creators would be central, accurate data fed into visual software, then interpreted through human imagination to make something emotionally resonant. The result would often be more about human perception than about raw measurements. On a deeper level, the event would invite revised myths and rituals, new stories to tell children about the night sky, and renewed philosophical inquiry into our place in the universe. Some will find the sight terrifying, others will find it consoling, a reminder that the cosmos is alive in its own, slow ways. The waking of such a giant can become a mirror for human behavior. Do we panic? Do we joke? Do we gather and make art? Likely all of the above. It would be an opportunity to practice humility and creativity at once, to turn data into meaning, and to remember that while the cosmos operates on vast scales, human reaction is immediate and richly textured, sometimes solemn, sometimes silly, often beautifully human. Odds and probabilities: how likely is a big outburst? The center of our galaxy hosts a very large black hole that usually behaves like a sleepy volcano, quiet most of the time, but it does throw off small bursts of light now and then. Telescopes watching it routinely see brief flares in infrared and 10th rays. These are like little sparks when you stir a campfire. Those small flickers are common and expected. A truly massive outburst, the kind that would turn the galactic center into a bright beacon across the sky, is a much rarer animal. A big eruption needs fuel and a trigger. If a substantial chunk of gas or a star gets too close, the black hole can slurp up a lot of material quickly and light up. Think of it like pouring a bucket of water on a slow-burning grill. The flare-up can be dramatic. Stellar winds from nearby stars and small gas clumps feed the black hole constantly but at a very low rate, more like a trickle from a leaky faucet than the deluge needed for a fire hose effect. So while the ingredients for a flare are present, the right mix for a major blast is uncommon. Estimating how likely a large event is at any given moment is tricky. Astronomers base their judgments on years of monitoring and on physics models of how gas moves and loses energy, but the record we have covers only a tiny fraction of the black hole's life. That means predictions come with genuine uncertainty. A useful everyday analogy is predicting a house fire by watching a single fireplace for a month. You might see sparks, but you won't know whether a full blaze will ever start. Models disagree on details, and small changes in the environment near the black hole can shift the odds a lot. Putting the pieces together, the practical takeaway is straightforward: frequent small flares are normal, but a truly major outburst is not something we should expect tomorrow or next week based on current observations. Long-term, the possibility exists because the right conditions can happen. Nature is creative, but it's not a constant threat. For comparison, it's like the difference between the pop of a charcoal grill and a bonfire. Both come from burning stuff, but one needs far more fuel and the right circumstances. So keep enjoying the night sky and your outdoor plans. The galactic center is more likely to entertain than to upend them. How this scenario refines our view of cosmic evolution. Sagittarius A** sits at the center of our galaxy, and today it is mostly quiet, swallowing only trickles of gas. If it flared up into an active phase, that burst of activity would behave like the bright cores we see in other galaxies, which scientists call active galactic nuclei, a fancy name for a black hole that lights up because it is feeding gas and dust. Watching that switch flip in our own backyard would give direct, concrete evidence about how black holes interact with their surroundings instead of relying only on distant snapshots. Think of it like finally seeing a nearby factory turn on after only ever seeing its distant glow through fog. The biggest change to our view of cosmic evolution would be how much weight we give to black hole feedback, the idea that energy emitted by a feeding black hole heats, pushes, or removes gas and thus controls star formation. Right now astronomers debate whether black holes mostly shut down star birth by blowing gas away or sometimes trigger it by compressing gas like a gardener tamping soil. Observing Sagittarius A** become active would let us watch that process in real time, showing whether nearby clouds are heated and dispersed or squeezed into new stars. That's a lot more convincing than guessing from a single photo. It's like testing whether a neighborhood sprinkler makes lawns brown or green by actually turning it on. On a technical level, an awakening Sagittarius A** would let models of galaxy growth be checked and tightened. Computer simulations include many assumptions about how energy couples to gas, how jets and winds travel, and how magnetic fields and cosmic rays behave. Many of those assumptions are tuned to match distant galaxies because we can't yet see the small details at great distances. Seeing the physics up close would be like opening the hood of a car rather than deducing the engine from the sound it makes on the freeway. Astronomers could refine how quickly black holes grow, how often they flare, and how those flares influence the buildup of stars and chemical elements in a galaxy. That in turn sharpens our whole timeline of how galaxies mature. Finally, the practical payoff would ripple through many areas of astronomy. Better calibrated feedback ideas change predictions about where stars form, how galaxies stop forming stars, and how gas moves in and out of galaxies, all things used to interpret surveys of the distant universe. It would also force a reality check on many theoretical shortcuts, making future predictions less like educated guesses and more like reliable weather forecasts. And yes, scientists would probably argue about the details over coffee for years, which is their favorite hobby. Lessons learned for living in an active universe. Sagittarius A** sits at the center of our galaxy, and if it ever became noticeably active it would send out bright flashes of energy and streams of energetic particles that travel far across space. Earth's thick atmosphere and magnetic shield already block a lot of this high-energy stuff, so we would likely feel effects mostly through our satellites, radio signals, and, in some cases, increased electrical currents induced in long conductors. That basic fact tells us the first lesson: know what protects you and what doesn't, and treat space weather like any other natural hazard. Designing for resilience is not glamorous, but it works. Satellites and spacecraft can be built with tougher electronics and software that goes into a safe, low-activity mode when warning signs appear, much like putting your phone on airplane mode before a storm. Power grids benefit from breakers and segmented lines that limit where surges travel, and utility operators can preempt problems by reducing load. People do this routinely when a hurricane approaches, so the playbook already exists. Simple, everyday examples help. A surge protector on your home router and a generator in the garage are small steps that mirror the protections engineers put on a larger scale. Personal safety and public health measures matter too, and they are often straightforward. Breaks in satellite communications mean navigation and timing services can be unreliable, so analog backups, paper maps, mechanical clocks, and distributed decision-making are useful. Increased radiation at high altitudes calls for common-sense adaptations. Flight crews can reroute away from polar paths, and critical workers might limit exposure. Underground or heavily shielded spaces reduce risk because rock and concrete stop a lot of harmful particles. Think of it as putting fragile items in a basement during a thunderstorm, practical and effective. Early warning and continuous monitoring would shape how society reacts. Telescopes, radio arrays, and space weather observatories that track high-energy events give authorities time to tell satellites to switch to safe mode, airlines to alter routes, and power companies to brace for disturbances. Public alert systems that are clear and tested, like those used for earthquakes, floods, or severe storms, help avoid panic and enable orderly responses. Clear, repeated drills make the response feel normal rather than theater. Community-level planning and simple preparedness pay dividends. Stockpiling essentials, maintaining local medical and communication hubs, and training volunteers for technology outage scenarios are practical steps. Local governments can develop black start plans for electricity, and businesses can test manual or offline modes for critical operations. That's similar to how shops prepare for seasonal power cuts. Humor helps morale. Keeping extra batteries and canned food will get you farther than a tin-foil hat. Foil won't protect electronics, but a metal box will, in fact, act as a Faraday cage. Finally, an active universe is a shared challenge that rewards cooperation. International data sharing, pre-agreed protocols for spacecraft safety, and coordinated public messaging prevent conflicting actions and reduce unnecessary risk. Scientists, engineers, policymakers, and communities working together create practical playbooks that borrow from everyday disaster planning, redundancy, drills, clear roles, and backup systems. Living with an active cosmos is less about science fiction drama and more about steady, sensible preparation, like packing an umbrella for unpredictable weather, but on a cosmic scale. Open questions that would keep astronomers busy for decades. Sagittarius A** contains about 4 million times the mass of the Sun and sits roughly 26.0 light-years from Earth, so the first big question is simply, what raw material would feed an outburst? Astronomers would want to know whether a sudden flare-up comes from a single big meal, like a gas cloud or an unlucky star getting too close, or from a steady rain of smaller clumps. Think of it as the difference between someone dumping a bucket into a sink all at once and a slow, dripping faucet. Both fill the sink, but the timing and splash are very different. Pinning down the origin of the fuel matters because it changes everything we can expect to see, from how bright the center becomes to how long the fuss will last. How matter actually turns into light near the black hole is another puzzle that would keep researchers up at night. The flow of gas is twisted by gravity and magnetic fields into a hot, glowing disk in some cases, but not always. Astronomers would want to know what controls the switch between a quiet, dim black hole and one that lights up like a beacon. Observers would compare quick flickers to long, steady glows, much like trying to tell whether your neighbor is starting a campfire or launching fireworks. Determining the heating and cooling processes, how particles gain energy and then radiate it away, requires combining simple observations, brightness and color, with complex physics, and that combination leaves many open threads to pull on. If powerful jets or outflows appear, their makeup and reach would become prime mysteries. Some jets are packed with fast electrons, others carry heavier particles too, and the difference matters for how radiation and cosmic rays spread through the galaxy. Detecting neutrinos or very high-energy photons from the galactic center would help, but it is hard to link those messengers definitively to activity at Sagittarius A star. Scientists would also ask how far the black hole's influence extends. Could it compress nearby clouds and trigger new stars, or would it blast them apart and shut down star birth? The question is practical. Feedback from the center can either nurture or kill star-forming regions, like a bonfire that keeps campers warm but can scorch the grass if it gets out of hand. Long-term monitoring and theory would go hand in hand, and both are full of challenges. Telescopes across radio, infrared, 10th ray, and gamma-ray bands would need to coordinate like a very slow-motion orchestra, while neutrino and cosmic ray detectors play percussion in the background. At the same time, modelers would struggle to simulate extreme gravity, tangled magnetic fields, and the chemistry of gas clouds all at once. It's like trying to film a thunderstorm from inside a tornado while also predicting the weather a month from now. The payoff, though, is huge. Answering these questions would not only explain what an active Sagittarius A* does to our own galaxy, but also teach us how black holes shape galaxies in general, a detective story with the Milky Way as the crime scene and astronomers as stubborn sleuths who won't let the culprit go free. So, quick recap: if Sagittarius A, the big black hole at the center of our galaxy, suddenly woke up and started gobbling gas, it would put on a spectacular cosmic light show. Think brighter flares, possible jets like cosmic squirt guns, and lots of radiation that astronomers would drool over. Because it's 26,000 light-years away, Earth wouldn't instantly fry. This is more amazing telescope footage than end of barbecues. We might see changes in radio signals, learn a ton about how black holes behave, and get neat aurora-like effects in theory, but life here would keep going much like before. If that sounds both terrifying and awesome, that's exactly why we watch the skies, to turn cosmic mysteries into stories we can understand. Imagine it like a campfire. If you toss on a big log, it flares up and throws sparks. From a safe distance you get warmth and a good story, not disaster. If you enjoyed this trip to the galactic center, please like, subscribe, and tell me in the comments what if you want next: a nearby star going supernova, a rogue planet crashing through the solar system, or seeing a black hole eat a star up close. In the next video we'll dive into one of those and see what would really happen. Thanks for watching, keep looking up, and don't worry, your next barbecue is safe.